Give me a second. Perfect. All right. Just a quick reminder of today's event. We will begin with a presentation by Nikita Dhawan, who is the main author of a publication at ICML, and she will be sharing with us this publication on efficient parametric approximations of neural network function space distance. This will begin very promptly at 10:40 until 11. After that, we will have 5 UTMIST projects from 2022 presenting their results for an hour or so. And following that, we will have Michael, who is the main author of a ICLR oral acceptance multi-rate VAE. And he will be sharing the results and details of that publication at 12:20. After that, we will have 3 more UTMIST projects from 12:45 to 1:30. And finally, we will end today's event with some futures of UTMIST projects and some details on how interested developers could join in the fall term of 2023. Just some quick information about UTMIST. If you are not familiar, we are a club that started in 2017, striving to really help out the ML community at U of T. Currently, we have 9 departments, 150 associates, including more than 70 project directors and developers. This year, we have 12 projects, including 5 company collaborations. And during this event today, we will have 8 projects presenting their results. On top of projects, we also have our medium publication, Demystify, which has more than 34 articles since September of 2022. We also host a lot of events for our fellow schoolmates at U of T, including our first hackathon, Hack the Mist. Lastly, we've had some really amazing social media growth this year, all thanks to you guys. And we really hope that this trend will continue on in the following years, so our work could benefit more U of T or even other undergrads from other schools. And finally, we will introduce our first speaker of the day, Nikita, who is a PhD student in the Department of Computer Science, advised by Professor Roger Gross, which is also an advisor for UTMIST, and Chris Madison. She is interested in self-supervised learning and trustworthy machine learning, including problems like robustness to shifting data distributions. Today, she will be sharing her work published in ICML 2023, which quantifies and estimates differences between related neural networks with applications in continual learning and influence function estimation. So Nikita, if you're ready, I will give you host access and you may guide us through your presentation.
Sounds good, thank you. Share screen. Okay, let me know if you can see my screen. Okay, great. So yeah, thanks for that introduction. I will be presenting my work called Efficient Parametric Approximations of Neural Network Function Space Distance, which was done in collaboration with Sheldon, Johan, and Roger. I'll abbreviate this to the acronym for our method, which we call LAFTER, and just for ease. So to begin with, the motivation for this paper was this question: given any 2 neural networks, how different are they from each other? And and there are several reasons why we might care about this. One would be continual learning. Continual learning is a setting where you are training sequentially on different tasks, and because of the shift in data distribution, something known as catastrophic forgetting is likely. So we would like to measure how much the neural network has changed in its distribution compared to a previous version of it, so that we can quantify the forgetting of previous tasks. Another application is influence functions. There's been recent work that has shown that influence function estimation is very related to how different neural networks are in their both parametric and output spaces. And we would like to measure how different a neural network that is trained on one data point versus not on that data point are different. And then lastly, another application is machine unlearning, in which case we want to take any data point and make sure that a neural network has unlearned that data point or no longer has information related to that data point. And again, measuring how different these two networks would be with or without that data point is relevant. So with that motivation, one potential answer for this could be that we can measure some discrepancy between the parameters of the network. So we vectorize these parameters and then try to measure how different those vectors are. There are some immediate issues with this. One is that parameter space can be very high dimensional. So if you have these very high dimensional parameters for neural networks and you try to measure something like a L2 distance, it's very likely that basically any 2 points in this space would be more or less equidistant from each other. So we wouldn't quite get a meaningful estimate of distances between the networks. And also we do just care more about the outputs of the networks. We generally use these networks to evaluate on some inputs, and then we want to see how different their outputs are. So with that motivation, another potential answer is to measure discrepancy between the actual functions represented by the network. And by that, what we mean more formally is a discrepancy in the network's output space. So whatever outputs it generates, given some input data distribution, and the two parameter vectors that we're considering. Throughout this presentation, and if you do read the paper, function space is basically synonymous with output space. So that's good to keep in mind. So to define mathematically what this function space distance is, which we will then try to approximate efficiently, it is the distance between the outputs of two neural networks. Here I say distance, more accurately we should say discrepancy, but I'll just stick to distance now because the example that I show will be Euclidean distance. This distance is measured by a metric in the output space. So could be Euclidean distance, could be KL divergence, and that is computed in expectation over the input chaining distribution. So that in math looks like this. If you have a function f that is represented by this network, and two sets of parameters, θ0 and θ1, we would like to measure its outputs on an input x, which is drawn from some data distribution p data, and then measure you use the metric rho to measure the difference between the outputs of these two networks. And that we're calling the function space distance between θ0 and θ1 given data distribution p data. Okay, so just in practice, we usually don't have access to p data, so we approximate this with its empirical, with the empirical average over the data set that we have available, say of n points. Okay, so to estimate the function space distance, there are several methods that have been proposed, and we can broadly categorize them into parametric methods and non-parametric methods. Parametric methods depend heavily on the parameters or some information related to the parameters of the network only. So they store all that parameter information and not any data along with it. So they generally have a lower memory cost. Non-parametric methods do need to store parameter information and also some information about the data points or the data distribution, and generally incur a heavier memory cost. Parametric methods generally regularize in parameter space, and non-parametric ones try to regularize networks in function space or output space. And in practice, at least for continual learning, parametric methods tend to have poor performance. And intuitively, that kind of makes sense because they don't usually take into account the data distributions that they're computing these estimates on. And the state of the art for continual learning has been non-parametric So non-parametric methods do tend to perform better. Okay, so in this paper, our goal is to come up with a parametric estimate for function space distance, abbreviated FSD, which is computationally efficient and memory efficient, but also performs competitively with non-parametric methods. And there are several advantages of having a parametric estimate, even outside of efficiency. One is that if you don't need to store too many data points, then that alleviates some kinds of privacy concerns also. So that's generally an advantageous thing to do. So I'll lay out the problem setting specifically for an MLP with ReLU activation functions. This work also generalizes to other architectures. For instance, in our paper, you feel free to go ahead and look at the generalization to convolutional networks. But in this case, I'll just present the MLP version to understand more easily. So if this is the definition of an MLP, we have pre-activations for every layer, which are a linear function of the activations of the previous layer. And then activations are computed as phi of the pre-activations. In this case, we'll assume phi is the ReLU function. This is a standard definition. And there's one more thing we need to define for our setting, which is what output metric we'll be considering. So like I said, we'll use Euclidean distance. And Euclidean distance can be written out as the sum of the first two moments of the outputs that you're measuring this distance between. So if Z is the output of the neural network and delta Z is, say, Z0 minus Z1, where those two correspond to outputs of the networks theta 0 and theta 1, then the expected Euclidean distance can be written down in terms of this expression, which is the first two moments of these delta Z's. And that becomes relevant for efficiently computing this distance. So the actual method is what we call linearized activation function check, and what we apply to the networks. So the key idea is that given two networks, we linearize each layer of the networks, specifically of the second network. If you pick some ordering, so pick one of them and linearize each layer of that network with respect to its inputs about the first network's values. Linearization has been used in some of these settings already, and specifically for continual learning. And generally what people have done is they linearize the network outputs with respect to the network parameters. So entirely linearizing the function in terms of parameters. But we do something different where we do this linearization with respect to each layer's inputs. So it's a layer-wise linearization. And we're not assuming any linear relationship with respect to parameters. So the nonlinear interactions between parameters still hold. So what this looks like in practice is that the first two lines here are network computations for some network theta 0. So those remain exactly the same as before, the pre-activations and activations. For the second network, theta 1, pre-activations still remain the same because they're already a linear function of their inputs. The activations are now this first order Taylor expansion of the activation function, the ReLU function here, with respect to its inputs, S0, about the first network. So that's where the 0 comes from. I'll pause here if there are any questions about this key idea. This is mainly the idea of the paper.
Hi, Nikita, just a quick interruption. Do you mind admitting some attendees in the waiting room?
Sure. Yeah, I see that. Okay, it should be good.
Perfect, thank you.
Okay, if there are no questions, I'll go ahead with how we actually implement this in practice. So if just a reminder that the Euclidean, so is there a question or anything? Okay. Just a reminder that the Euclidean distance that we're trying to compute, we only care about these output delta Z's. And we can write that down for each layer's outputs. So these deltas for each output. So delta S is, this is just algebraic manipulation that I won't go into, but delta S is basically a function of the activations that go into this layer and the delta of those activations. And similarly, delta A is just a function of the deltas of the pre-activations. So we actually have this structure where we can propagate the deltas through the network. And specifically, we only care about the moments of these deltas. So we can just propagate the first 2 moments of deltas of every layer's outputs in order to get the delta Z finally. So just to take a step back and see why this is a good idea. So I hinted to a few of these things earlier. One thing that I said already was that nonlinear interactions between parameters are preserved in our case, unlike any other method if people are familiar with the neural tangent kernel, where the linearization of the network is done with respect to parameters. So they convert, that kind of approximation converts the network to something that is linear in its parameters. In our case, that's no longer true. So we allow nonlinear interactions between parameters, which could be important for performance and what the networks actually represent. Second, the network is linearized with respect to its inputs, and that actually allows for this moment propagation idea because we're able to leverage things like linearity of expectations, and we can do it using only moments and don't actually have to store any data points to evaluate the network on. And lastly, the expected FSD estimate is actually computed with just a single forward pass. In general, if we were storing data points and then had several batches of data points on which we wanted to compute these network outputs and then measure a distance, it would take several forward passes, and depending on the problem setting, could be computationally pretty expensive. But in our case, it only takes a single forward pass to do this computation, which is nice. Now, to actually implement this in practice, we need last 2 approximations to get an entirely parametric estimate. And in this case, in the case of MMPs, we call this a Bernoulli gated linear network. So the first approximation we need is to actually come up with the inputs to the first layer. So we can use, we can model the data distribution as a Gaussian, compute the moments of the inputs to the first layer are the data. So we can, which is why we need to model the data distribution as something. We can compute the moments of the data and sample from this multivariate Gaussian. The other thing that we need is the derivatives of the ReLU activations. These show up in the linearization, the linearization approximation that I had earlier. So because these are ReLU activations, they also have the structure being either 0 or 1. And so we can model these as Bernoulli random variables. So instead of passing pre-activations through a function phi, we multiply them element-wise with this Bernoulli random variable m. And the same thing holds for the deltas as well. One thing, and this m is a Bernoulli random variable with some mean parameter mu. Specific to layer L. One question is that how do we actually compute the average masks of these ReLU activation functions? And I won't go into too much detail here because I'll skip ahead to results after this, but one thing is that we could just compute the mask, whether it's a 0 or 1, based on the signs of the pre-activations that we already have. And in the paper, the results corresponding to this are called laughter. And the second way we can do this, if we do have the allowance in terms of memory and storage, is we can maintain a running average of how many times any given unit was a 1 or was left on during the training, and use that as the Bernoulli mean parameter. And that's what gives it this Bernoulli gating structure, and we call it BGLN. So I'll skip ahead. This is just summarizing sort of the algorithm that I already went over. So just to quickly go over it, all we need to do is store moments of the data and these Bernoulli mean parameters, sample from whichever random variable we need for each layer, and then propagate those samples through the network and compute a distance between the outputs at the end. And this actually becomes an unbiased estimate of our laughter-based FSD. And this is just representing that in terms of the actual computations. There's also a deterministic version of this that we can compute because we're only propagating moments. We can, instead of sampling from random variables, just use the moments of those random variables and propagate those through the network. And in that case, we can get an expected distance between outputs. This is useful for settings where stochasticity is not helpful. So it's nice to have a deterministic version of it. And again, these are computations that I will skip over for now, but they're all explained in the paper as well. One last thing that we evaluate is having class-wise estimates. So in typical classification setting, for instance, all these random variables that we're using to approximate different information are done for, so far we've done them over the entire data distribution, but we could have a more fine-grained estimate and make all these approximations for each class. And that just multiplies our storage costs by the number of classes that we have. But it also gives us gains in performance. I'll just admit people. Okay. So how do we know if a computation is expensive? Is a specific metric you use. So one thing that we use is computationally, just we can measure the number of forward passes. That's not very complicated in our case because we actually just use one forward pass. In terms of memory costs, I'll skip ahead to the results that show this. So we can actually analytically, in the last column here, for each method, we can analyze what the memory cost for each method is. So in this case, P corresponds to the number of parameters of the network, and is the number of data points that a method might use to store, might store and then use to compute the FSD. And D is the dimensionality of the data. So, and C is the number of classes. So depending on your problem setting, there would be, some of these would be more expensive or not. Some are obviously very cheap just in general, but some of them are more or less expensive depending on what these exact values are. So we found that in these typical settings, like for continual learning, on this C400 benchmark, we have pretty good gains in memory. There are more results on this in the paper showing the percentage gains over other methods, while also, maintaining that goal that I mentioned earlier, where we have competitive performance with other methods and achieving state of the art on these. I see I'm out of time, but I'll just say quickly that there is some analysis on the different measures for how well we're estimating function space distances. So if anyone's interested in that, I encourage you to go and look at the paper. But essentially the point here is that we show that we're closer to the true function space distance than other methods would be. And this idea of linearization with respect to inputs actually helps a lot for that. And lastly, I'll just show quickly results on influence function estimation. This function space distance term actually shows up in influence function estimation, which is something that was shown by a previous paper from our group actually. And we sort of just use it as a test bed for our method to see if this can help in the setting as well. And the advantages in this case are that a typical way to measure this term for influence function estimation would be to iterate through your entire data set and compute this function, this term for the data set corresponding to P chain. In our case, it's just a single forward pass. It's computationally much cheaper. And this is a case where there's some solvers for influence function estimation that don't handle stochasticity well. Which is why our deterministic estimate actually performs quite a bit better. these are the results for influence function estimation. The main takeaway here would be that we have higher correlations than other comparisons to the high correlation to the true objective that we want to estimate when we use our laughter-based approximation called BGLND here. And this, the plot on the right is a further application of influence function estimation in finding the fractions of corruptions or detecting corrupted data points. And again, while being very efficient, our method, the BGLN method, does get very competitive performance with other methods which actually iterate over the entire training data set and aren't as efficient. So yeah, that is the end of all I wanted to share. And I'm happy to take questions now or in the chat, or also feel free to email me if you'd like. But yeah, thank you for listening.
Thank you, Nikita. Is there any questions from the chat or our audiences?
I don't see anything in the chat for me.
There's no question, then once again, thank you so much, Nikita, for the presentation and your time. I'm personally really interested in the paper. I'll probably give it a much deeper read and chat with you later on or something. Do you mind sharing your email perhaps in the chat? So if there's anyone that's interested in your work or just any personal advices, they could reach out to you.
Yeah, definitely.
Perfect. All right, let me share my screen. For this showcase, there is one. Actually, let me just give you a quick, I'll show you quickly over here. This is the most updated itinerary. And following Nikita's presentation, we will be getting into the project showcase where there's 5 projects coming up. All right. Our first project will be Wall Street Bots Crypto, which is a continuation of our 2021 project, Wall Street Bots, with a focus on cryptocurrencies this year. And this year, they've compiled a much more detailed data set to predict volatile crypto prices through innovative features engineered for market data and social media sentiment through Twitter. Without further ado, let's invite Lisa, Fernando, and their team to present their work. And I believe I could allow screen share without giving host access, if I'm not mistaken.
Yep, that would be great. Thank you, Stephen.
No problem. Give me a quick second. Could you try sharing your screen now? Perfect.
Okay, awesome. So thank you all for being here today. I'll give it to Lisa to start presentation.
Sounds good. Hi, everyone. Wall Street Bots 2 is a continuation of last year's Wall Street Bots project. And the goal this year is to predict Bitcoin prices using machine learning. Next slide. Here's the agenda for the presentation. We'll go over the background for the project, how we created the data set, what machine learning models we used, and each of their results, and finish up with some concluding thoughts. So last year's Wall Street Bot project predicted the prices of meme stocks like GME using sentiment analysis on Reddit posts. The main limitation we found was that we had a lack of high quality publicly available trading data for stocks. So for this year, next slide, we decided to predict the prices of cryptocurrencies instead, as their prices are determined purely by supply and demand, which should make them more predictable by analyzing public sentiments and market data. So the project structure here is we first obtain market data features and NLP data features separately. Then we train models based on each set of features. And then we try to combine the best models from both streams. Next slide. So we looked at some research regarding the usefulness of sentiment analysis being applied to market, specifically of predicting Bitcoin prices using Twitter sentiment. And also the application of LSTM in market modeling was found to be one of the best models.
So how do we create our data set? So we started off by creating hypotheses for which data should have predictive power in the trading price and why. And then we cross-checked the data against the lagged Bitcoin returns using correlation analysis. So these are all our features. And the only ones I wanted to highlight were the Bitcoin block data and the book and trade data, because they were the only ones that had significant non-zero correlations with the returns. And on the left-hand side here, you can see a snapshot of the order book data. And you can think of the order book data as just a list of trade orders that haven't been executed yet. The left-hand side of the order of the snapshot is how much someone is willing to buy for. You can see that in the green. And on the right-hand side is how much someone is willing to sell for. And this is further divided into levels, where level 1 is the best bid price, and you can see 477 units are available or people have 477 units available to buy at 2,167.75. And on the flip side, there's 290 units of sell orders at 2,168. And where the level 1 prices meet in the middle is the current average selling price. And this data is available on a second-by-second interval. And that's the raw data that we collected. But what's important is that we just use the level 1 and level 2 data. So in this case, it's just the first two. So if you look at the bid prices, only 2,167.75 and 2,167.5. That's how much we went up to. And we also used the trades data, which is an aggregate of the trades that occurred over a second-by-second interval. And this gave us some insights into some statistics like the mean and the median sell price. And as you can see on the right-hand side of the slide, we can derive a lot of features from the order book data that aren't fundamentally there. For example, we engineered the bid and ask spread and the bid and ask strength. The feature engineering process in this situation was mostly a combination of data exploration and using intuition and domain knowledge to figure out what works and what doesn't. Next slide.
So in terms of NLP data, what we did was we didn't have a single data set. So we scraped 100 Twitter per hour per coin. So we're analyzing a few different coins to a range of 3 years. This is a quite big data set that will cost, I think, like $250,000 nowadays to collect if we use the API. We did with our own scraper. So the one extra thing we did was after we collected the data set, we filtered for bots using some heuristics that we found. Like if you have a lot of following and very few followers and post a lot, you might be like a spam account. So we want to remove that. Once we had this data set, what we wanted was to create we want to aggregate all the tweets with a sentiment score. And to do that, we use 2 pre-trained models, so Vader and Google T5, to get scores for positivity, negativity, happiness, sadness, anger, fear, and surprise. So we got this whole spectrum of sentiments, and we also aggregated this in like different time intervals because to test what was best, because sentiments might affect the market in the future. So sometimes 4-hour lags can be better than 1 hour. And also we added like change in each score as a feature, and all the features can be found here. If you want, there's more details about it in our Medium article. I'll pass back to Lisa to talk about the ML models.
Thank you. So yeah, we trained 9 models on different sets of features to predict the log return of Bitcoin at time t+1. The baseline model is the simple moving average model, where the next predicted return is basically the average of the previous n values. This gave directional accuracy of 50.6% and MSE as shown. And we fitted, for all the different models, we fitted ARMA on only historical returns, SVM, XGBoost, and LSTM on sentiment data, and linear regression, LSTM, and hidden Markov model on various market data. The best model for the sentiments data is LSTM with directional accuracy of 56.5, and the best model for market data is also LSTM, fitted on book and trades data with directional accuracy of 67%. Next slide, yeah. We want to further evaluate the best models thoroughly using more than just the directional accuracy. Specifically, we looked at the financial metrics such as the empirical performance of a portfolio trading based on our predicted returns and the Sharpe and Sortino ratio of such a portfolio. And we also looked at statistical metrics like directional accuracy, MSE, confusion matrix, and F1 score.
So when we want to evaluate our model, the answer to that is kind of multidimensional. It's important to understand the successful model from both a scientific lens as well as a financial lens. So first up, we have a 50-second snapshot of the log returns over time in the top left-hand corner. And as you can see, the predicted returns in red hug the actual returns in yellow very closely. And the overall trend of the returns is captured by the model. As well, the mean squared error for the log returns, for the predicted log returns is on the order of 10 to the -9. So it confirms that we have very low error in our predictions. So next we want to explore what would happen if we created a portfolio and actually executed the trades based on our predictions. If we predicted positive returns, we would long Bitcoin, or we would buy it. And if we predicted negative returns, we would short it or we would sell it. And we assumed that we had no other trading fees or other costs associated with this. And what we got was a return of around 500% over the course of only around 5 minutes. As you can see, the timeline goes up to 3,500 seconds. At the same time, the price of Bitcoin was largely stagnant, and we beat the returns of just holding Bitcoin along the same time period by 47-fold. The blue and yellow lines show the long and short Bitcoin benchmarks. So the short Bitcoin benchmark being that we short Bitcoin for the entire period of time. As well, the Sharpe ratios and Sortino ratios were 0.32 and 0.48. Having close to 1 for the Sharpe ratios is excellent, but anything over 0 is also considered pretty good. And next up, we have the confusion matrix. And for those of us that don't know what a confusion matrix is, imagine a COVID test. A common misconception is that a COVID test only has 2 outcomes, positive and negative, but in reality it has 4. False positive, true positive, false negative, and true negative. A confusion matrix just puts these statistics into a square format to make it easy to read. And in this case, the matrix is also heat mapped, color-coded based on the number. As you can see, the true positive and true negative predictions take up the majority of the data. They're around 1,000 data points each. And they both occur in largely the same frequency. So there's no positive or negative bias. So this is an indication that our model is unbiased and accurate in its predictions. And we also calculated the F1 score, which turned out to be 0.625, which confirms this. So overall, we have a raw directional accuracy of 67%. And the histogram down in the bottom middle here shows that the density of wrong predictions along the log returns kind of reaches its peak when the log returns are around 0. And this is because when the price doesn't change much, it's difficult for the model to differentiate actual movement from just noise. So that leads to reduced model efficacy. And then finally, we have a scatter plot of real versus predicted returns. Ideally, we would want both of them to be the exact same, following a linear y equals x trend. But obviously that's impossible, but we can come close. And as you can see, the data follows that trend quite well. So the real and predicted returns are quite similar. And I'll leave it to Fernando to talk about the NLP side of things.
Oops, so I was muted. So thank you, Sujit. So we have here the same graphs, however, for the NLP data. So here we only use the features that we collect from Twitter, as we talked a little bit before. I won't go into detail for every graph just because Sujit did a wonderful job on explaining all of them. But I want to highlight a few differences. So first thing is, as you can see, the quality in general of these results is a little bit lower compared to the market data ones, because we're not using any information about how Bitcoin is like varying. We're only using sentiment for the market. So sometimes, for instance, we have in the bottom center plot, like a log return that is actually very negative and we predicted wrong. However, that said, we still have a quite good portfolio return, as we can see in the middle, like the center figure of the top row. We outperform shorting and holding Bitcoin by significantly, like 6 times. That's quite good. And we still have a directional accuracy of like 56%. There's also one extra advantage that is worth noting about using the NLP data is we don't trade that often. So we're trading every hour instead of like every second. And the advantage is we reduce a lot of the trading costs that are part of the limitation of this project. So trading costs are very reduced for this when compared to market data returns. The Sharpe ratio for this model is also like around 0.15, which is not great, but is also not that bad. Now let's discuss a little bit more what are the next steps and limitations of this project. So a few project limitations. One is that like analyzing real-time data and doing, especially for high frequency trading, is very hard and it's still not implemented. So it would be a big step if we wanted to continue implementing the strategies in the real world. Also, as I mentioned, trading costs are very significant, especially if you're trading at high frequency. And it's something that we see in our models, like 47 times returns, which is crazy. But if you consider trading costs, these returns are reduced by a lot. We cannot include that in our model because your trading costs will vary depending on which side of the trading you are doing. So if you're doing as us, it will cost something. If a bank is doing, it will cost way less. So another limitation that we want to discuss is scraping data in real time is hard. It takes time. And now Elon Musk is implementing some changes that make it even harder. And the API prices nowadays are crazy high. And as I mentioned before, if we wanted to collect the data that we have, like using the API, it will cost $250,000, which is not in the budget for UTMIST, I think. So as some next steps of the project, we want to like merge, as we said, the two models that we have. They both have quite good results. So we believe that if we find a way of merging them, which is a challenge because they have different frequencies. So one is second by second, the other was like hour by hour, or even like 4 hours by 4 hours. Merging them is hard, but if we can we believe that we can achieve an even better model that might get the best of both. It's also, as I said, hard to analyze the different frequencies. And finally, one next step they want to do is understanding the relationships between features to actually get insights about the about how different features influence the model. Right now, we get very good models, but we still cannot explain which features are causing our results to be great. And that's something that we want to explore in the future. I think that concludes our presentation. Thank you so much for listening, and we're open for any questions you have.
I think there are some questions in the chat, so I'll start off by answering some of them. So one concern is trading cost and the frequency at which we're trading. So yes, right now, like the reported charts and everything, the results is based on very high frequency trading. And yes, this would give pretty high trading costs, and we haven't accounted for those in there, and which is why we list it as a limitation. So it's more unlikely for retail traders to implement this strategy, and more likely for research purposes and for high frequency trading firms like market makers, hedge funds, who have lowered trading costs just inherently because of their business. So it might be more applicable in that sense. But also, if we want, say, to trade it retail wise, what we can do is increase this cutoff for when we make a trade. So in other words, if we predict the return to be high, but like higher above a cutoff, or low but lower than a cutoff, then we make a trade. In that case, we are more with the same level of confidence, but we are predicting a higher, like a greater absolute return. That way we can capture more return with less risk. And we actually did run some simulations using that. So if we use a cutoff of just like a little bit above 0, we were able to get a Sharpe ratio, or actually let's use Sortino, because Sortino only penalizes downside risk, and that got us around 2.8 for Sortino ratio, which is a really good value. And you can see that, like, if we play with the cutoff, you're able to lower the trading frequency, so only trade when you predict really large movements.
I think I want to answer another question by, I think, Tiona. It's in the chat, like, can we apply this for the stock market? I would say that was the idea of last year's project. So if you take a look at what Wall Street Bots did last year, we were trying to predict the stock market using Reddit data and also market data. As we mentioned at the beginning of the presentation, so I can go back here, there are some limitations of that, mostly with how much data we can get, credible and publicly available data. So that makes it a challenge. But I think overall our strategy, there's nothing in our strategy that's too specific for cryptocurrencies. So analyzing sentiments and using powerful machine learning models is something you can definitely do for the stock market. It's just you need the right data, and that's not always as easy to get as for crypto.
And also for the last question, whether or not we tried to use embeddings and directly pass into MLP. So I guess for embedding, if you're referring to the sentiment embeddings or market data embeddings, well, either way, it's a possibility, and we did try that last year, but with that, it's reduced explainability, and we want to focus on more like feature driven, as in all the features that we selected, inherently there's a reason for, or intuition based on market intuition for why it should work. And we also did a correlation analysis and found all the features that we used to be highly correlated. So I think that inherently would be able to give us higher accuracies.
Well, I think Steven said there is no more time for questions. Again, we appreciate the time and the attention for everyone. Great questions. And thank you so much, Steven, for UTMIST, for giving us the space to talk about our project here. Yeah, have a great day.
Thank you so much, Fernando and Lisa and your team. It's a wonderful, really, really wonderful project and a really great presentation. And yes, if there's any more questions or further discussions, please be encouraged to contact Fernando or Lisa through Discord or through UTMIST for any further discussions. And this is a quick glance of the entire team for this year's Wall Street Bots Crypto. Moving on, we will have our second team, DiffMuse, which created a novel model for generating polyphonic classical piano music through unconditional generations, utilizing recent SOTA architectures such as diffusion models and state space layers. This project is led by Austin, Walter, and Elliot. And they will explain this project in a lot more detail and provide you with some very, very interesting sample audios that they've generated.
All right. Thank you, Stephen. I'll start off. Let me share my screen here. And I also have to be careful to share it with sound because we will have some samples. All right. Which screen am I sharing? 1 second. Perfect. Share. All right. Can you guys see my screen? Yeah. Say yes. Good. All right. So yeah, we are DiffMuse. So our team is Alston Lowe, Elliot Schreider, Walter Merjo, and Anatoly Zavyalov. All right. So the motivation of our project is for composers to have an aid that they can input some part of their composition, some melody idea that they have, and have a model essentially fill in the remainder of that melody or suggest new ideas. This isn't a real example. This is Chopin's Ballade No. 3, but this is sort of the vision we had when we were starting off.
Hello, I'm Walter. Our problem that we are trying to solve, or I guess what we're trying to do with DiffMuse is generate classical polyphonic piano music in MIDI format. So basically multiple lines of melody and on a temporal level, as in like when a note is pressed and how long a note is pressed. So this time is not in beats or anything, it's in pure milliseconds, for example. So we don't have time signatures or tempo or any of that stuff. It's just the time the note was pressed and how long it was pressed. And our model has focused on unconditional generation, meaning just from a blank canvas, just generate a piece of music for this fixed amount of time. Though we just mentioned that we wanted to complete a composition, we'll show later that it's possible to create a post hoc conditional generation out of a model that does unconditional generation like DiffMuse. And so some related works here that we've been looking at while making DiffMuse. We have the music transformer work by Mittal and SDMuse. And I guess our ultimate goal is to dethrone the music transformer as the state-of-the-art music generation model. And we plan to do a listening study with people and calculate metrics on our music, which we will also go into depth very soon.
So now I'll provide some details about our approach. So we train on the Maestro dataset. So this is a dataset of about 200 hours of paired audio and MIDI recordings from 10 years of a piano competition. And basically, I think they use a special piano to record when notes are played, and they have actual performers playing. So importantly, the data from the Maestro dataset isn't really annotated with things like tempo or beat, as Walter said earlier. But the MIDI files that come out of it are have very high accuracy. Next slide. For our architecture, we use a diffusion model. This is a very popular type of generative model that has achieved state-of-the-art in especially the computer vision field. At a very high level, a diffusion model, it iteratively noises samples, and then it learns to reverse the process and by reversing the process, you can basically create structured examples from complete random noise. And as for architecture, we draw from some of the recent state space literature, which has provided these layers that are capable of very long range sequence modeling at very scalable complexities. And so in terms of our actual data representation, we diffuse over these note arrays. And basically a note array is this sequence of notes where each note is represented by 4 values: the pitch of the note, the volume, the duration, as well as the delay. And the delay of a note is basically the offset time from when the note is played in comparison to the preceding note. And we found that this data representation worked much better than something like a raw piano roll. It's definitely much more compressed, and we were able to get better quality samples from using it.
Yeah, so as Walter alluded to earlier, we can use a unconditionally trained diffusion model to do post hoc conditional generation. And basically the algorithm that we used is one from one of the related works. And I won't go into the details of the algorithm, but essentially we can sort of modify the reverse the denoising process that the model was trained for, and modify it in such a way that we can sort of mask out one part of a sample and then have it filled in by using this algorithm. And so if you want to like either infill, so if you have a part in the middle of the piece that you want to generate some variation, you can do that. Or yeah, we can also sort of try and apply this to continuation. And now I'm going to talk about metrics. So comes to metrics for music models, there has not been sort of much research in this. There aren't standard sort of metrics that that papers use. If you look at some of the related works, they all use something sort of different, or they may focus on listening studies or just some very basic metrics. In fields like computer vision, we have things like Frischet inception distance or inception score, which are these very good metrics that are independent of data representation, independent of the model architecture, which are supposed to assess the quality of, say, like an image generation model. And similarly in NLP, we have something like Blue Score for assessing quality of translations. And in particular, one of the metrics that some previous music models have generated is the negative log likelihood, which we can't produce with our model. Diffusion models can't produce that. So we've found difficulty comparing 2 previous models since that was one of the main metrics that they were using. And it's just sort of hard to find metrics that, you know, capture the musicality of a piece, doing so quantitatively. But there are some that there has been a little bit of work in this, which I'll talk about now. And so essentially, there are a couple of papers about trying to develop some metrics for music models. This is sort of the main one that we found to be the most impactful. It's from this paper on the evaluation of generative models in music. And so what this model what this paper does quite well is it gives a bunch of absolute metrics. So meaning things that you can musical related things that you can calculate on a piece, like pitch count, meaning like how many different pitches were used in this piece. You can have the average pitch interval, so like between 2 consecutive notes, what's the average interval. Pitch range, meaning like what was the highest pitch minus the lowest pitch, so how much did the pitches vary in the piece. There are also similar metrics for like note length. And we also have use some for volume as well. Another one that's quite interesting is this pitch class transition matrix. So I've included an image here from that paper. Pitch class transition matrix basically gives you probabilities of transitioning from one pitch to another pitch. So like so if your current pitch is E, or this is, yeah, for pitch class. So that means we're not worrying about which octave we're in. It's just, yeah, which of the 12 pitch classes. So if the current note is a D, what's the probability that the next note is an F? And you could look at this matrix, or that would be represented by a probability in this matrix. And then the important part is that we can use these to generate relative metrics, because these raw numbers alone don't allow you to compare two music models, really, because, you know, what does it mean to, like, there's no such thing as a good pitch count or whatever, like it's better to have higher or lower. That's, you know, so we can't directly compare models using these. So on the next slide, I'll describe sort of how this paper moves towards relative metrics. And so there's essentially a process, which is, so we take one of these absolute metrics, say pitch class. And what we do is so what we can do is we can generate histograms. So you'll see that there's a bunch of lines in this diagram. And so what we can do is, like, for each pair of data points in the training data, so like for the pitch count for each piece in the training data, we can compute like Euclidean distance and get like a histogram of distances. And then we can approximate that by like a Gaussian. We can also do that for the, for if we're trying to compare two music models, we can perform that process with computing like pairwise distances for one of these absolute metrics between model 1 and the training data, and then also approximate a distribution, and then also do that for the second model. So if you see here, the distributions I'm talking about is, you'll see this red line in the diagram was sort of a distribution now that represents one of our metrics for the training data, and then we have the green and the blue one, which are supposed to represent distributions for the two models. And on the next slide, I'll explain how basically you get metrics out of this. So we can compute the similarity between the models. So we have a distribution for model 1 and model 2, and one for the training set. And so we can compute the KL divergence and the overlapping area between the model 1 distribution in the training set and the model 2 distribution in the training set. And the idea is that if these distributions are more similar, then it means that that model 1 basically matches sort of the musicality of like what should be contained in the training set. And we do this for each of those absolute metrics. And so in this diagram here, you'll see like we have basically the so it's called sort of the intraset, the difference like between the training set examples. And then we have for the first model, the interset is referring to the difference between it and the training set, which is sort of the one of the distributions we use. And then for the second model, also the interset. You could ignore the intraset for the two models. And then, so what we're computing here is, you see in the diagram, the KL divergence in the overlapping area. So in this example, the overlapping area is higher for the second model. It's like 0.5 instead of 0.1, which is better. And the KL divergence is also lower. The paper explains in more detail why they use both of these. There are some scenarios where overlapping area can capture differences better than KL divergence can. But so in this scenario, we would say that MIDI net 2 in this comparison is better than MIDI net 1.
All right, now we're gonna play some samples. So we have the piano roll right beside the sample. So hopefully the audio will be audible. All right, that was the first sample. It was kind of a lot of counterpoint, kind of like a fugue. All right, let's listen to the second one. Now the third one. And the final one. All right. So after listening to these 4 samples, they have pretty coherent musical ideas, and they stay within a certain key, so they don't veer off. And most importantly, they have it's not mentioned on the slide, but these samples can actually be played by a person. So here you can clearly see that it's 2 hands playing. Here you have some chords that can be played with, well, 2 hands. And so this seems a bit less realistic, but this you could still play if you have some pedals and stuff going on. And we have a fairly consistent tempo in all of these samples, and they also have pretty expressive dynamics. So if you're wondering what the differences in color here are, these more colder colors indicate quieter, while the warmer colors indicate louder notes. And we picked these samples because they demonstrate a variety of different musical styles. So as I mentioned, this first sample is a bit more Baroque, you have a lot more counterpoint. This second sample was a bit, I actually don't know how to describe this one. Third one was a bit more classical, and the very last one with the big chords was much more romantic and much more expressive. As you've probably heard, it sounds a little bit choppy at times, and it does tend to forget what it was doing, and it also can be sometimes a bit messy, and there's a little bit of inconsistency in quality. So we did cherry pick these. All right. Thank you. Does anyone have any questions? So Mohammed asks,
I see a question about, could you explain the state space model more? I think it's quite hard to explain it concisely, but I can direct you towards like a repository that contains all the relevant papers. 1 second.
Maybe can I ask what kind of difficulties did you guys encounter a lot in this project?
I think a major difficulty was getting the data representation right, as well as the model right. We tried a bunch of stuff, and funnily enough, like the simplest thing worked in the end. Are the samples generated? The samples we showed here are generated unconditionally, but the model does have the capacity to do conditional generation. Any specific reason you chose the classical genre?
Sure,
I think the classical genre. Oh yeah, you can.
Sure,
take this
yeah,
another.
I can answer that one. Yeah, I think we chose the classical genre because it's well, we wanted to like originally like make sure to sort of restrict what we were producing enough so that we could have a better chance of having a more successful model. We did think about like wanting to expand as like we progressed, but with classical, particularly piano music, there's like more availability of classical, and it's like quite structured. Yeah, the availability of like data sets for other kinds of music could be more varied. Yeah.
Yeah, I would like to add to with classical music, some of these pieces, like they're quite complex. So I think it's also interesting to aim for this genre. Yeah.
Yeah, there's another question about added a metric to evaluate human playability. Yeah, we haven't done so yet. I mean, it would be probably somewhat difficult to even come up with some sort of like way to structure that into the loss, because you can't just simply do like how many notes are played simultaneously, because you can, if you use pedals and whatnot, you can have a very large number of notes like ringing at the same time. So it's very difficult to, and generally like it can do more harm than good to impose like extra constraints like that on the model. If you just because the data that's traded on at the end of the day is all from human playable pieces, and so as the model, if your model is reflecting that more and more accurately as you progress, then that should naturally happen. I think there's probably more harm than good that can happen by like adding that in, and because we've thought about this before with other things about like adding an extra like accoutrement to like the loss or whatnot to try and, when we were having difficulties having better sounding samples, but more often than not, it was the better approach was to do less and just focus on like having a stronger model, just like without actually messing with the loss. I think, yeah, the applications of the project. So yeah, our initial one is to, or the one we mentioned at the beginning, is to be like a compositional aid. So if you're a musician or a composer and you're writing a song and you're stuck or whatever, then you could use a model like this to generate some potential, continuations of your piece, and that might inspire some creativity. And so, we've thought about if this would be useful, and like once we're sort of we have completed our model, like to the point where we think we're absolutely done, then we've thought about if like making it, creating some sort of app or application or something where someone could actually use that. Let's see. Yeah, and that's I see that will be the last question, it appears. Yeah, because I think the next group has to go now. But yeah,
Thank you.
Thank you very much.
Thank you, Elliot, and thank you, the team of DiffMuse. It's a wonderful, wonderful project, and I believe you guys may be submitting or continuing the project. So wishing you guys all the best to any future endeavors or publications, perhaps.
Thank you.
Moving on is the team of Omni, which is a collaboration with a startup, Omniscience, to create a knowledge work power tool that automates and resurfaces and generates text using the most relevant lines from your personal documents, books, favorite websites, transcriptions, etc., etc. And for people that are interested in ChatGPT, you will definitely be interested in what this project and startup has been doing. And in fact, we're very happy to have one of the founders with us today, Jeremy, Mr. Jeremy. Thank you for joining us today. I hope the presentations has been enjoyable so far. And let us pass the time to, I believe, Matthew, who will be presenting for us.
Yeah, okay, let me just share my screen. Can you guys hear me? Computer audio. Okay. Yeah. Can you see my screen?
Not yet.
No, but you are sharing your computer sound.
Oh, great. Stop share. Give me a second. Here's where's sound. Oh, there we go. I think that's the one. Now can you see?
Yeah, it's good now.
All right, cool. Yeah, so this project has been a startup collaboration with Omni, and Omni is basically building power knowledge work tools, specifically with AI. And we set out to kind of, with UTMIST, create a tool that could use your knowledge to generate text. And so the motivation here is like, even though we started before ChatGPT was released, ChatGPT is released now, so it gives us better framing. It's not fine-tuned to your sources when you use ChatGPT. So it only gives you generic content. Let's say you want to write a long business report about something that requires a lot of information in your business. You'd have to manually input a lot of context into ChatGPT for it to understand what's going on and for it to generate something that's feasible. So it performs quite poorly on tasks that requires a lot of context. So to solve this, we wanted to create a system that used retrieval augmented generation. And so the team that we were really grateful to have consists of myself, Ian, Yanan, Kevin, and Jonathan. And a better way to give you kind of like an overview understanding of what Omni is this little video that some YouTuber put out about 2 weeks ago, where he explains the product pretty well.
So this is how its web app looks like. It has multiple panes like in Obsidian, and you're going to be mostly working on the left panel. Whether you're writing an academic essay or your next blog post, you can start writing here. But this is the cool part. As you write, it uses your writing as a query for your knowledge base and brings up relevant passages from articles and books. And then you can dig deeper into each passage if you need to see the context, which will be displayed in the central panel, and you can keep reading it if you like. And then you could also go to another book or article, but you don't have to worry about the ones you opened previously because it keeps a record at the bottom of the central panel, so you can always go back to where you were. Also, if you select a specific word, sentence, or paragraph, it will use it to find relevant information from your database. This makes it very easy to find the links between ideas because you don't have to manually search through your database, find the ones you're looking for, and then go back and forth between pages. But there's more. Like many.
Okay, yeah, so that little snippet showed you what the existing product was like before we started working on retrieval augmented generation.
So this is how it's web.
Let's skip to the next page. And here's just kind of like a brief summary of what he was showing you. The product, part of the product is this extension that kind of goes wherever you go in your browser. And whenever you select or type text on any web page, it'll instantly surface the most relevant lines from the files that you've uploaded. And so we already had a robust retrieval system. And so we thought, hey, we could hook this up with a generation system to make retrieval augmented generation. And here is a little demo of what we were able to achieve afterwards.
The favorite part of this app is that you can upload your own notes as a dataset too. So I used a note app called Logseek as my note app for a long time. So I uploaded its folder to Omni, which took like an entire day because I have thousands of notes, but it was worth the wait. I can now choose my notes as a dataset and browse them and find useful, relevant ideas as I write. Even ask questions and then Omni gives me an answer based on my notes. This is really cool because it feels like you have a GPT-3 that is trained with your own data. To me, this feels significant because with most of the existing AI apps, you cannot choose which dataset the AI is going to use. So what they generate is very generic, which is why I almost never use those AI apps for my own content. But this changes that because it can now use my own data to write, like how I write. Anyway, if you've been using
Okay, yeah, that's that for that little snippet. And so now let's talk a little bit about the architecture. We can't get into too much depth because I am under NDA, but I can give you like a brief overview of everything. So first, there's the upload pipeline. Basically, we accept uploads from Google Docs, Word docs, Markdown, Word files, text files, EPUBs, websites, and so forth. And when a user uploads those files, we write all that data to our database, and then we tokenize it and we convert all the text into passages. And then we embed those passages in batches, and we build an approximate nearest neighbors index from those embeddings for each type of tokenization. So we have several different types of tokenizations and several different types of embedding models, and we create an ANN index for each one of them. And then this is all stored to our database. And the next step would be the retrieval augmented generation step. And so in this side of things, the user essentially inputs an input string, and they've selected data sets that they would like to use. So that gets inputted in. And we found that actually, if we use a large language model to first give us a quick response, it actually improves the performance when we use that quick response to then search for retrievals. So we first generate a quick response, and then we input that response into the ANN retrieval, where we embed the input string, which in this case is the quick LLM response. And then we query our ANN indices for the nearest embeddings for each of the given data sets. And then we also retrieve some metadata and context that we've also built surrounding each result. And then we kind of clean things up, remove duplications, truncate, and return the top results that basically the results that have the nearest distance to the user's input string. And then we basically prepend these results to the user's actual input and give it as extra context and put it in a transformer model. And then the final response is the retrieval augmented generated response. And so when we got to this point, it was around January. So we decided, hey, you know what, maybe we can take things a little bit further. And funnily enough, I think this was not when ChatGPT was released yet. We decided to work on a chat, and then ChatGPT kind of blew up. And yeah, so I think you'll find this interesting.
At Omni, we've built ChatGPT for your documents. Let's take a look at a quick demo. Here we've uploaded Yuval Harari's book, Homo Deus, and we're asking about the job market in 2050. OmniChat generates a detailed essay using relevant lines from the book, providing deep insights into the future job market as predicted by Harari. As you can see, we can even click into the source to see exactly which lines Omni used to generate its responses. Need to switch context? Just open another chat. I select a dataset about note-taking and ask Omni why I should take evergreen notes. Omni searches through the dataset for relevant information, and then it generates a detailed response as to why you should take evergreen notes and what they are. And again, we can click into the source to see exactly which lines Omni referenced. Welcome to Omni.
Okay, yeah, a bit dramatic, but that's kind of what we got to more recently, and we have it up and running on omnilabs.ai/chat. So if you want to go test it out for yourselves, you can do so without even having to create an account. I'm pretty sure it's free for public use. Yeah, and then this is a bit after UTMIST ended. Here's just a bit of a sneak peek on what we're currently working on. We're currently working on book generation, so generating a 200+ page book with a single natural language request. And there's just like a screen recording that I did a few days ago where I ask quite like a, I guess, timely question. Write a book about the fourth industrial AI revolution, generative AI, how it might impact the job market, create job loss, and whether there's like a need to restructure society or explore potential solutions to job loss, such as universal basic income. And then I hit generate, and it takes a really long time because we're generating a book. And so I check my email. In a couple minutes, the email comes basically telling me that, hey, your book is on the way. And then in this next slide, we can see the actual generated book. And this is completely AI generated. And I was reading through it, and it actually kind of makes sense, which scares me. And you guys can read it yourselves at this link, omnilabs.ai/book/AI. If you guys want to check out the completely AI generated book, you guys can go there. And so at the moment, it's just it's only using a large language model to do this, not retrieval augmented generation. But we are also working on that because we think that that is when things get really interesting, when authors or writers can put in like their lifetime of work, their lifetime of like writings, and then use it to generate a new book or something. So yeah, that's basically all I have for you today. Any questions?
If there's no question at the current moment, we could still leave it to any further discussions after the event. But thank you
Sounds
so much,
good.
Matthew, and your team. It's a truly, truly amazing work. I'm personally always surprised by the demos and the videos you send me. So I'm really amazed by what Omni is doing right now.
I would also like to thank Jeremy for just coming and attending and giving us the opportunity to work on such an incredible project.
Absolutely.
Mohammed, that is not something that I would be able to answer. Maybe Jeremy could answer that.
Yeah, I guess we will inevitably have custom LLMs for private data. There are just so many people who can't send their data to OpenAI and Microsoft. So invariably we'll have models for them. And it will likely be the state-of-the-art open source as opposed to something we train in-house because it's very expensive to train and maintain these models. But if you maintain some high-quality infrastructure, you can scale whatever the state-of-the-art open model is. Yeah, you can scale that up.
Thanks, Jeremy. All right, if there are no more questions, thank you guys for your time.
Thank you, Matthew. And once again, I want to thank Jeremy too for providing UTMIST and our developers this opportunity. It's truly wonderful, and it's something that UTMIST would like to continue with Omni and also other startups in the future. All right. Then let's move on to the next project, which is 12-lead ECG reconstruction, which is also a startup collaboration with OnHand AI. Develop a ML model that can streamline the process of analyzing ECGs. They've experimented with multiple skeleton models like UNets and transformers and achieved a really high quality reconstruction of 12-lead ECG signals from only 2 to 3 LEDs as input. I believe Jason is in the call, and feel free to share your screen.
Can anyone see the screen?
Perfect.
All right, okay. We may begin.
Yeah, sure. All right, so good morning, everyone. Today we're going to present the ECG reconstruction project. We really appreciate you taking the time to watch our presentation. So without further ado, let's get started. Next slide, please. So first, I'd like to briefly talk about the motivations and goals of our project. Electrocardiogram, or ECG for short, measures the electrical activity of the heart. A complete set of ECG consists of 12 signals, yet measuring 12 leads of an ECG can be time-consuming and resulting in higher diagnosis rates. And this motivates us to design a machine learning solution to reconstruct the 12 leads ECG with only 2 or 3 leads of input to improve the data collection efficiency and reduce the chance of lead misplacement. Our project therefore aims to evaluate how well machine learning reduces the need for collecting 12 leads of signal, and if it can reduce the need for error-prone chest placement. And more specifically, we aim to develop a deep learning model that only uses signals from 2 or 3 electrodes and can synthesize the rest of the missing leads. Next slide, please. So a quick background about the ECG here. ECG is an essential first-line tool in the diagnosis of many different types of heart conditions. According to the Centers for Disease Control, more than 69 million ECGs are performed annually in the US during doctor's office and emergency department visits. Taking an ECG test requires a health professional to attach 10 electrodes, and these electrodes are used to generate what is called a 12-lead ECG. The accuracy of limb electrode placement does not have much impact on the signal. However, the location of chest electrodes, V1 to V6 on diagrams are critical. Studies have shown that even trained health professionals can misplace the chest electrodes. And one study found that only 10% of participants, including doctors, nurses, and cardiac technicians, correctly applied all the electrodes. And misplaced chest electrodes can change the expected signal and result in missing certain diagnoses. And this motivates us to seek a technical solution that can reduce the time and complexity of ECG collection and the risk of misdiagnosis. Next slide, please.
Yes, I will introduce about the datasets. To prepare the ECG signals for our training and evaluation, we use two public available datasets on the internet. The first dataset is this PDB-XL. It includes over 20,000 ECG signals of very high quality, and it has a variety of diagnostic, form, and rhythm labels. And the signals are sampled all at 500 Hz, and each lasts for 10 seconds. So each signals will have 5,000 data points. We split the train validation and test splits using stratified sampling over the joint distribution of all the labels. And the split ratio is 70 by 15 by 15. We'll use the same ratio for the other dataset. So the other dataset we are going to use, okay, next slide, please, is the code 15 dataset. So it's a publicly available subset of a private dataset called code. It contains much more ECG signals than PDB-XL, but the labels are fewer. It has in total 6 Boolean diagnostic labels. The signals are sampled at 400 Hertz, and the quality is lower. So first, some signals are very short and are padded with zeros. So padding is not very problematic for ECG classification, which is the why the dataset was created for, but it is not very suitable for a reconstruction test. So we remove the zero paddings and clip all the signals to 2,934 samples. And the second, some ECG signals contains extreme voltage values, usually appearing at the end of the signal when the leads are detached from the patient's body, which cause large losses or even nans in our models. Some other signals are too noisy to be useful. So we discard these low quality signals when we're storing the dataset. There are more pre-processing steps in the runtime as follows. So as shown in the next slides, so in the runtime, both the input and the output leads of a signal are passed through a Butterworth filter, allowing only frequencies between 0.5 to 60 Hertz. This filter first removes high frequency noises, and second, low frequency baseline vendors. Removing baseline vendors is very important because if we fail to do so, baseline vendors will become the main contributor of our model losses. So after this, we perform the mean normalization. However, we're not going to do standard deviation normalization because if we do so, the amplitude relationship between different leads would be lost, and the trained model turns out to be worse. So here's an example where an original signal on the left gets preprocessed and become the signal on the right picture. So we can see that the removal of baseline vendor greatly improved the signal quality, despite some minor artifact can still be seen in the chart drop. And that's, yeah.
All right, so before we introduce the machine learning models, it's worth noticing that the first 6 leads of ECG signals, lead 1, 2, 3, AVL, AVR, and AVF have linear relationships. So as long as having the information of 2 out of the 6 leads, we can compute the rest 4 signals with very high accuracy. So instead of training a machine learning model to reconstruct these leads, we decide to compute the remaining leads, giving lead 2 and lead 3. So the machine learning models discussed in the following presentation only serve for the reconstruction of the last 6 leads of ECG, i.e. lead V1 to lead V6. Next slide.
So we implement 5 models in total. The first one is a simple linear regression model, a single linear layer with no activation functions. The model learns a linear mapping between the input and output. We chose to implement it first due to several reasons. So it's simple and fast to train and serves as a good baseline. Also, linear regression is interpretable. This helps us identify and verify the linear relationship mentioned in the previous slide. Another natural fit for processing temporal data is the long short-term memory model. So LSTM is capable of learning long-term dependency and patterns in temporal data. And next, we implement a convolutional neural network. The CNN consists of a stack of 1D convolutional layers, each followed by an activation function. Every layer will have an increasing number of output channels, and the number of output channels in the final layer equal to the number of output leads. One thing worth mentioning is the use of seam padding. This is to ensure that the output size matches the input size, so that the length of the reconstructed signal is the same as the input signal. So every Con1D layer extracts local features from the reduced CGD signal, and then utilized by subsequent layers to form high-level features. So as CNN models show good performance, we then tried a more complex and capable CNN-based model, the UNet model. The UNet model consists of an encoder and decoder. The encoder network downsamples the input, while the decoder network upsamples it back, and in our case, reconstruct the missing lead in the process. The architecture is designed to capture both local and global context information. Our implementation of UNet uses 1D convolutional layers instead of traditional 2D convolutional layers for image segmentation tasks. So while UNet is good at capturing local and global context information, not all time instance of the ECG signal is of equal importance. Therefore, as we all know, attention is all you need. So as a next step after UNet, we want to try a transformer-based model. And transformer is a sequence-to-sequence model based on the attention mechanism. Similar to UNet, it also has an encoder and decoder. However, the vanilla transformer didn't perform as well as we expected. It didn't capture the local context information as efficiently as UNet. Therefore, we improved on the model and designed a hybrid model that combines the strengths of both UNet and transformer. The hybrid model, UNetformer, as we call it, wrapped a transformer inside the UNet, as we can see in this illustration. The UNet will encode the input, pass the result to transformer, and then reconstruct based on the output of the transformer. And this hybrid model achieves the best performance among all the models we implemented. Yeah, next slide, please.
Yes, so for all the 5 aforementioned models, we use the same and the most commonly used loss function, i.e. the mean square error, which performs good enough for us. And we have 2 additional metrics for the accuracy of reconstructed signals. So to measure the absolute differences between the reconstructed and original signals, we use the root mean squared error. And to measure the relative differences, we use a Pearson correlation coefficient. Yeah.
So for experimental setup, we first want to find the best input leads. So it's proper to have 2 leads from the first 6 and 1 lead from the back 6, so that the first leads can be perfectly reconstructed using the linear relationship. And after testing the lead combinations, lead 2, 3, and V3 are the best, and we use them as the input for the rest of the experiment. And then we tune the hyperparameters for all models except for linear regression, as it has almost no parameter to tune. We search 120 hyperparameter sets for each model for 16 epochs on the PTB dataset. And we use the Optuna framework to tune our model. So finally, after we obtain the best hyperparameter for each model, we train the models for 32 epochs on PB and 16 epochs on CO15. And this number of epochs are just enough for the model to converge on each dataset. On the right shows an example of how we configure the hyperparameter tuning. So with the aforementioned method, we obtain our model results on 2 metrics for each data set. And we also recorded the G-flops to represent the computational complexity for each model. And as a general review, UNet and UFormer are the 2 top performing models, with UNetformer outperforming UNet by an average of 0.5%, which is pretty low. But in terms of computational complexity, UNet former is 38.9 less than UNet, which makes it more favorable than UNet for same level of reconstruction quality. And before we go deeper about computational complexity, we observed that model performances in PTB is generally better than CO15, which agrees with the fact that PTB is much cleaner than CO15. For linear regression, despite its extreme low computational cost, it drops 39.44% from PTB to CO15 in terms of performance. And now STM is also very efficient, but it still has some room for improvement that cannot be compensated through hyperparameter tuning. So for UNet former, it leads other models by a larger margin in CO15 than PTB, which means that it's more robust to noise than other models. And therefore, we suggest that model with high computational complexity or high expressivity is still very necessary for a decent reconstruction. So for visualization, the blue lines represent the ground truth signal, and the red line represent the reconstructed. In this 6 image for the first 6 leads reconstruction, you can see that lead 2 and lead 3 doesn't have a red line because these are just the input leads. And as we mentioned before, we used the linear relation to reconstruct the first 6. So it ended up having a really perfect reconstruction, which is shown by the red lines almost perfectly matching the blue line, as you cannot see any like blue colors on the like image with the red lines. But for the back 6, so for example, we use a LSTM to show us some example reconstruction for this sample. We can see that there's a certain gap from here and there between the red and the blue, which are the indications of the reconstruction error. So we want to compare the model reconstructions, and then we realize that we can obviously see the reconstruction error, the gap between the red and the blue for the linear regression and the CNN, and for LSTM, UNet, and transformer, the gap is more obvious when the signal is noisy. So here's the reconstruction visualization for PTB-XL, and it's for V6 of a sample. And as you can generally see, our models, like all the models presented here, seem to have a similar level of reconstruction. And this is because PTB-XL is generally very clean. But for CO15%, we can immediately see that there's a mismatch for the reconstruction of linear regression to the ground truth. And if you look closely enough, you'll find that the UNet former is actually having slightly better reconstruction than LSTM and UNet. Yeah. And there concludes our results for the models. And for next steps, we may want to train with larger data set to further improve the reconstruction accuracy and reduce the loss. And we also want to reconstruct 12 lead signals with only 2 input leads.
So yeah, that's the end of the presentation. Thank you for your time. We also want to thank UTMIST who organized today's event, and Hand AI, who's the collaborator of our project and provided research guideline and valuable feedback to our results. So yeah, thank you for watching, and we are open to questions.
There's no question, then thank you so much, Jan and Jason, and your team for the really great work for the ECG reconstruction team.
All right, thanks.
Moving on, we will have Michael, who is our invited guest, to present his ICLR oral acceptance on multi-rate VAE. Let me quickly give you guys a brief introduction to Michael. First of all, thank you, Michael, for joining us today. And I personally really look forward to your presentation. Michael here is a 5th-year PhD student at U of T and Vector, who is currently supervised by Jimmy Ba and supported by NSERC CGS Fellowship. He is interested in improving our understanding of neural networks and developing algorithms which are theoretically motivated and works across a broad set of problems. Today, he will be presenting us his ICLR oral publication, multi-rate VAE in short, which is a computationally efficient framework for learning optimal parameters corresponding to the trade-off between reconstruction error and the KL divergence rate in a single training run for VAEs. So Michael, if you are ready, feel free to guide us through your publication.
Great, yeah, thanks for the invitation, and yeah, I'm excited to be here. I'll share my screen. Okay. Can you see my slides?
All good.
Okay, great. Yeah, so I guess just one quick comment is I did a similar organization during my undergrad, so it's really exciting to see people do the same thing here and to hear about all the cool projects going on. So today I'll be talking about multi-rate VAE, which we published at ICLR, and I'll talk a little bit more about, I guess, some of the motivation for the work throughout this presentation. And if you have questions at any time, feel free to interrupt and I'll pause a couple of times through the presentation. Okay, so the main idea here is, I guess we'll start with some background. So originally the motivation comes from autoencoders, which if you're not familiar with, the goal of an autoencoder is to learn a latent representation, which is smaller than the original sized input, which captures key features of the input. So in an example with MNIST digits, we're trying to reconstruct a 4, but we have this intermediate bottleneck layer, which is much lower dimension. No, and this is a standard autoencoder. Typically, we have multiple layers of a neural network that encode the input into this bottleneck, and then we decode the output afterwards. So one tweak we often make to the autoencoder is we also want to enforce a constraint on this latent variable z to make it more meaningful, meaning currently there's no constraint at all on z, and it can just be any d-dimensional vector. But if we constrain it instead to be similar to a vector sampled from something like a Gaussian distribution, this gives us some more structure in this latent space. And one key advantage of that is it turns this autoencoder into a generative model, meaning to generate a new example, we can just sample from our latent variable and then run it through the decoder, and that gives us a new generated output. So that's the standard structure of the variational autoencoder. And essentially now there are two losses. So there's this original loss, which is the same as what you typically see with the autoencoder, where we try to reconstruct the input to be as close to the input as possible while also reducing its dimensionality. And then there's the second term known as the KL divergence term, where we typically constrain our latent variable distribution to be as close to a Gaussian distribution as possible. And one really popular framework for training this VAEs is, there's a question. Okay, never mind. So one typical framework is to use the beta VAE objective, where beta is some positive constant that trades off between these two terms. So greater beta would put more emphasis on the second term. And yeah, so this is a beta VAE objective, and it's commonly used in a lot of text and image generative models. So one problem with this approach, though, is that to train for a given beta value, you have to reinitialize your network and train from scratch. This is objective, and it's not clear a priori on a new task what beta value to choose. So the standard VAE chooses a beta value of 1, which we denote with the star here. And various different values of beta will result in different values on what we call the rate distortion curve, which is essentially like how well you do on the two different losses. So on the left here, you see various trade-offs, and these correspond to training from scratch with different values of beta. And on the right here, this is from the Celeb A dataset, which is a dataset of celebrity faces. You can see what the generated outputs look like for various values of beta. So we get various trade-offs, and the typical way we describe these trade-offs is if we have a low distortion value, that usually means we can reconstruct the data points well, but oftentimes the data points that we generate from scratch are unrealistic. Whereas on the other extreme, if you have a low rate, that means the variational distributions may be close to the prior, but we may not have actually encoded useful information to meaningfully reconstruct the data. So this is a challenging problem, and typically tuning the KL weight beta depends on every application independently. Okay, so that's a motivation for the problem. Let's see if there's questions. Okay, I don't think there's any so far, so we'll move along. Some additional background information is we'll now describe the idea of a response function. So the response function is something that maps from a KL weight beta to the optimal encoder and decoder parameters that minimize the beta VAE objective. So you should think of this as we train to completion with a given value of beta, and that gives us a variational autoencoder. And we're trying to learn this mapping from this single beta to this high dimensional space that encodes like the optimal parameters for that beta. So this is sort of the objective that we're actually trying to learn in our new framework. Pictorially, it might be a little bit more clear what's going on. So for each of the values beta, we get a loss surface corresponding to, I guess, each of these dimensions, where the loss surface represents the weights of the encoder and decoder. And we're projecting into a lower dimensional subspace. And you can see there's a particular value that minimizes the loss for that given value of beta. And this value changes as we vary the value of beta. So the idea of the response function is we want to map from beta to this projection that essentially slices through different values of beta. So rather than training from scratch, we want to ideally be able to learn this red curve here. And our goal is to do this in a single training run. So that's the key intuition behind our paper. Like, we have all these different beta parameterized losses. Can we try to learn this in a single network? So the way we approach this is we parameterize something known as a hypernetwork, where it's a small modification of a normal standard network, where the standard network we refer to as the base parameters. And essentially what we're doing is for each layer, we also have some hyperparameter condition layers, which scale the base layer. So the idea is these hyper layers take in our value of beta, and then they tell you how we should modulate the base layers to produce the desired response function. So in equation form, we take a log of the beta because beta is typically sampled from a log uniform space. So if you sample beta uniformly, you got to take the log, and then you perform a linear transformation and apply an affine function. Then you row-wise scale the base weights, or element-wise scale the bias term. And this is like our modification to the standard base network. Another way to think about this is if you write it out in equation form, normally you have the next pre-activation is equal to the weight times the current activation plus the bias. What we're doing here is we can actually decompose this into the product of two terms. So you have the base network, which is fixed across every single beta. And then depending on the sort of beta objective that we're trying to minimize, we apply this transformation, which applies like a gating. So we're basically gating each layer based on the beta that we're trying to optimize. The picture form of this equation is this applies to every layer. And what we're doing is normally you have your input X, it goes through your layer and it generates some output. What we're doing now is for this output, we're applying this element-wise gating. It's sort of similar to what you might do in an LSTM, where this gating factor is determined by the transformation of the beta term. So essentially, this gives knowledge to the base network of what hyperparameter and what objective we're trying to tune. And the advantage of this approach is it's only a small additional number of parameters. It's roughly 3 to 5% to represent response functions on many VAE architectures. And the reason we're motivated to choose this type of parameterization is if you study the linear case, you can actually show this can exactly represent the optimal response function in linear VAEs. And we show through our experiments that it's actually pretty good for more complicated architectures and tasks as well. Any questions here? Okay, let's keep going. So this table essentially shows like how many parameters the base standard network has versus our Mr. VAE architecture. And you can see the increase in the number of parameters is relatively small. So we can obtain this potentially expressive architecture with only a very small number of additional parameters. Okay, so next I'll describe our training objective. So we have this architecture, but it's not able to actually learn anything unless we define an algorithm for how to train this architecture. But the procedure isn't actually too challenging. So the key difference between training a Mr. VAE versus training a standard VAE is now we are trying to minimize this expected loss, where the expectation is over this choice of beta you're sampling. So our goal is to minimize sampling from this log uniform space, this loss across all different beta objectives. And this is analogous to what's used in self-tuning networks, if you're familiar with that. So the actual modification to the algorithm is actually very minimal. So the red parts are the augmented parts. So as usual, you would sample random mini batch. And the difference here is you also need to sample from your hyperparameter sweep space. So we sample a beta term essentially, and then this beta determines the loss for each of the examples in our mini batch. So actually during our forward pass, we can choose a different loss function for each of the individual betas. And it also determines how we condition our hyper network. So once you do that, you can actually calculate the loss given the current parameters. And then backpropagation actually just works very naturally. So it's going to backprop to the base parameters, and it's also going to tell you how you should update the hypernetwork parameters to best modulate the network. And then we take our gradient update as usual. So it's a very minimal change to the typical algorithm you use for training hypernetworks. For training standard networks. And that's our algorithm. Okay, so we'll now describe some results. So here we show the standard rate distortion curves as you've seen before. And our comparison is sort of to training a lot of different beta VAEs with different betas. And this corresponds to these triangles, which are upside down here. And you get various different values on the rate distortion curve. One thing with beta VAEs, though, is you oftentimes actually need to do some sort of scheduling on the KL terms as well. So we show that in the upright triangles. And then the red curve, which is actually a continuous curve, shows the results of our Mr. VAE algorithm. And one key advantage of our algorithm is actually you only get 8 points here because you've only done 8 runs, but you can actually plug in any value of beta because we're sampling from this continuous space. And actually just gives you different trade-offs on this rate distortion curve. So you can see the parameter count, training 8 beta VAEs is 8 times the original parameters, but we have a very small increase, and the training time is slightly increased because we have some more parameters we have to do backprop through. And we also get an entire rate distortion curve rather than just points along the curve. So this really has a lot of advantages over training a lot of different beta VAEs from scratch. And you can do this same experiment across a lot of different tasks. So we show results on various different benchmarks with image and text data. And we also scale up to NVAEs, which are a recent architecture that generates pretty high quality samples. So this basically shows that we have an efficient algorithm now to like, rather than training from scratch and then repeating this many times to get your best beta VAE, you can just train this Mr. VAE architecture once, and then after you've trained, you can just pick whichever beta you want best. And the way you pick that beta can be based on like the quality of the generated samples, for instance. So on the left, you see examples generated by beta VAEs trained from scratch. On the right, you can see the results of our algorithm and how the quality varies across different betas. So one interesting thing to note is that if you're training from scratch, there's no similarity between the different betas. Like the latent space doesn't have this property that we have here, where if we use the same hidden latent vector, we actually get semantically really similar outputs in the generated space. So for a given image, you can sort of change its sharpness or its contrast just by choosing a latent vector and then tweaking the value of beta. So these are results on slob A, and this is like the street house numbers data set. If you have some other downstream objective you want to tune, you can also do that as well. So sometimes people care about metrics such as the FID score, and you can tune that just by plugging in different values of beta and then getting the value of your metric out. Finally, one nice property is that we do have to specify our sampling range, like where we're sampling our values of beta. And we show in our experiments how we're robust to this choice of sampling range. So if A is a lower bound and B is upper bound, we run experiments where we either fix A and vary B, or fix B and vary A. And you can see that the resulting rate distortion curves tend to overlap. So there's not too much like meta hyperparameter tuning you have to do by choosing how to specify A and B. Okay, yeah, so that's basically the results of our paper and some experiment details. I guess I'll just end by saying, like, this wasn't the original direction of our project. Like, we initially were just trying to tackle like a family of different tasks, and we're trying to do this Pareto frontier sort of approach where you want to get as best as you can on two different metrics. But it turns out that it seems to be slightly easier to tackle if you actually have two objectives that are slightly competing. So in this case, the two losses, they're sort of in conflict with each other, which makes it a better sort of problem to tackle with this hypernetwork-based approach. And we've been lately working on trying to generalize this to just standard supervised learning as well. So you can try to tune hyperparameters with such as like dropout or L2 regularization without like training a bunch of times from scratch as well. So I think that's an exciting direction for future work, like figuring out where you have objectives which are conflicting or mutually like they share some similarity, but there's some conflict between them, and then trying to apply this sort of framework. Thanks for listening. Okay, so one of the questions in the chat is, what are the downsides of this approach? I think if you're scaling to a very large data set, it might be the case that our architecture isn't expressive enough to capture like all the intricacies. So like our rate distortion curve might be slightly shifted from the optimal rate distortion curve. But on the sizes of the data sets that we studied, like on this slide, it seems to generally be as good as training a bunch of networks from scratch or better. So I guess you can see like this triangle here, this isn't a point we can necessarily obtain. So you can do slightly better sometimes by training from scratch. There's another question, which is, are there specific data types where this approach is less effective? I think, I guess on the project we're working on right now, where we're trying to tackle more general problems, one thing we've noticed is it sort of depends on your choice of architecture. Like currently with our setup right now, we're applying it after essentially every layer, but depending on whether you're using like self-attention mechanisms, it's not as clear where you want to insert your hyper layers. So there might be various trade-offs depending on the architecture you're using. On all the image tasks though, it seems to work pretty well. Okay, another question is, does it mean that it's also hard to tweak the latent vector and potentially get a semantically similar but visually different output, such as a face? Yeah, so that's a good question. I guess one way to tweak the latent vector is you can actually encode an image that's similar to the one you want to generate, and that gives you a latent vector you want to sample from. And because the latent space is somewhat meaningful, you can potentially apply some small amount of noise to that random vector and then regenerate. And that's one potential algorithm for generating similar inputs. But it might be the case that you might want to use a completely different paradigm, like VAEs might not be the best approach if you're just trying to generate semantically similar outputs.
I'm guessing there's no more questions. Then thank you so much, Michael, for the presentation and your time to join us today. We really appreciate you spending time with us, listening to the presentations of other projects. Hopefully it was enjoyable. And once again, thank you for your presentation.
Of course, yeah. Thanks, everyone.
Moving on will be our fifth project of the day, Virtual Creatures, which is a team that created a articulated body system in C# embedded in a custom Unity environment that generates and evolves a recursive virtual organism, analogous to a robotic design. Their system could be served as the basis of a universal evolutionary algorithm playground for numerous applications. It's a very, very exciting project. There's a lot of visuals for you guys to enjoy and some very exciting outlooks, including perhaps collaborations with Unity. So let me now pass the time to the team that created this beautiful playground for some beautiful creatures.
Yeah, thank you for the intro. Hi, everyone. I'm Andrew, and I'm here to present to you our Virtual Creatures project alongside Carol, Efe, and Anoop. So we're working on basically an evolutionary algorithm for robotic design, as was stated, and we'll just get the rest of our team here, and then let's get into the background.
So from the dawn of civilization, humanity has been looking for more and more efficient ways of locomotion, of moving stuff from point A to point B. And nature has been at this for way longer than us. And it seems to be very good at generating these very interesting, unique creatures that perform these different functions. So what we're going to be doing today is that we're going to discuss how we used evolutionary algorithms, as well as some other algorithms to generate creatures similar to how Carl Sims did in his 1994 paper called Evolving Virtual Creatures. We're going to talk about combining reinforcement learning, which is a more modern and efficient algorithm to generate creature brains, and how we combine these to create interesting forms of locomotion. So there's many different applications of this project. So you could look at nanomedicine, such as proteins and how they move along different structures and protein motion. NASA's used evolutionary algorithms to generate antennas with the minimum number of amount of material possible. We have drone evolution, designing and controlling drones. We've also got designing and controlling walking creatures that might be going on off-road environments. And the applications of this virtual creature system is just very vast.
So we can also look at a couple of results from the original paper. We've got some very cool paddling motion seen here for the swimming environment, as well as some various types of walking motion, including some rowing and a worm-like thing. And then we've even got more complex mental behavior in target chasing, where we're going towards a vector position that's variable. We've also got some re-implementations of this work through something called the 3D virtual creatures evolution. And this is one of their kind of prime evolutions, which is the end over end worm. It kind of has a similar worm-like structure, but it's been discontinued. So what we're kind of working on is making our program more accessible, public, and just generally updated with modern technology. So let's get into this. What's our algorithmic basis? How are we tackling this issue?
The main crux of this project is an evolutionary algorithm. So we're going to be starting off with an initial population of, in our case, creatures, and testing them to see which ones are best at going, in this case, swimming. And we're going to be keeping the best ones, getting rid of all the rest, and mutating and crossovering the creatures that are the best in each generation to make it so that the next generation is incrementally better. Over time, the fitness is going to converge on a certain value, and we're going to receive our final, essentially, locomotion method, our perfect creature.
So here's how we've actually implemented this. For the first generation, we randomly generate a batch of 300 creatures, which you can see here. Then we evaluate their fitness, which in our case is their displacement. This is a reward that they're trying to maximize. Lastly, we keep the top 20% of the creatures, we kill the rest, and we mutate their genotypes. Note that the number of offspring of a creature is proportional to its fitness, so the most successful creatures make the most children. Then just keep repeating this process. We generate the phenotypes, we evaluate the fitness, and we select and mutate the genotypes. Finally, we stop the simulation once the fitness begins to plateau.
So some background information on reinforcement learning. So reinforcement learning works by having a learning agent interact with an environment. The agent gives an action to the environment and observes how it responds with its current state and reward. And the agent then chooses an action to take next that maximizes the reward and sends that action to the environment. So in this feedback loop, the algorithm learns from its own mistakes without the use of a data set.
And there have been plenty cool works done with reinforcement learning. We've got some awesome results from DeepMind in terms of locomotion. We've got some cool results from OpenAI involving hide and seek, where we have agents competing with each other to get better reward. We've got fantastic board gaming engines in terms of AlphaZero. And then we've got a more recent paper in soccer playing robots, where the robots not only learn to move their own bodies around and not fall over, but also control a ball against an opponent. So overall, the kind of really advanced behavior that can come out of reinforcement learning and the lack of a data set means that we're able to most likely use this algorithm to augment what came from our past work. So let's get into that. How are we actually doing this in Unity? Well, first of all, we have our combined algorithm. And what this is it's basically an evolutionary algorithm where we look at our morphological changes, going from something quite simple into something more complicated and efficient. And then we basically remove the entire brain and replace it with a reinforcement learning agent. This is to be implemented. Our project for this year was implementing the most hard to prototype part, which is the evolutionary algorithms written entirely in C#. There are plenty of Python libraries for reinforcement learning, and those connect directly into Unity. So we've left most of this as it's architecturally there, but it hasn't been trained yet. But to explain it, it would be basically a very similar multi-layer perceptron that works according to something like a policy gradient or along those lines. Our simulation and reward are relatively straightforward. We're trying to optimize for kind of efficiency of our app. So we've done a approximate linear fluid drag using the velocity of each face, the normal of the face, as well as some coefficients for drag, density, and surface area. Our fitness function has been adapted to an RL context by having it be a per frame reward. This is done by looking at the displacement of the center of mass with the dot product of the direction of travel. So this keeps the creatures kind of going in a set direction.
So how do we actually represent these creatures? So what we have is we have a set of two different, essentially our parameters, which is our genotype, as well as a physical representation of creatures, which is part of the phenotype. So we have the system of nodes and edges, which represent this the parameters of the creature. Each node represents a segment, and each edge represents the essentially the muscles and the connection between segments. We have a neural structure as well, along with this creature, where we have different neurons which take inputs either from the environment or from other neurons, and their outputs feed into essentially what strength each muscle is going to have and if it's going to contract or relax.
We also have a mutation process for these graphs. It's in 5 different steps. We first start off by mutating the parameters of each node. So this could be making a segment slightly larger, maybe changing its color or its shape. Then we add in a new node to the graph. This is disconnected at first, and it kind of allows our creature to grow in size and change its morphology. Then we add in new connections. So we basically mutate our existing connections parameters. We can change the orientation of a part or change its position on the creature, all that stuff. Then we retarget our connections. Children are passed around, parents are passed around, and different parts are connected in different ways. And then finally, we do garbage collection. We don't want the graph to topologically expand into infinity, and so we just, prune it down. This process is done for both the physical side of things and the neurological side of things.
Each running of our algorithm, each time we start a simulation, is going to generate one creature. So that is what it's going to eventually converge to. The fitness is going to converge to is it's going to be one creature. But as we run this multiple different times, different starting conditions, different mutations, end up leading to very diverse and different types of locomotion, different creatures. And as you can see here, that there is, it's very good at exploring the space of all these different types of motion in either swimming or walking.
So let's get into those results.
Yeah, so what we can see here are some of the interesting walking creatures we obtained. These creatures on the top use two segments that self-intersect to push themselves forwards, which is really interesting because it's learned to effectively use oscillatory motion to propel itself. And this is a surprisingly simple design. Like we expected to see legs or slithering appendages, but it just traded pieces self-intersection, which is effective, but we think it's a bit too simple. So we're going to add a constraint to block self-intersection to get some more diverse creatures in the future.
Now we're going to look at creatures evolved in swimming environments. The creatures here converge toward a one body and two limbs that act as paddles design. They move in a periodic time asymmetric movement, which means that going forward looks different from going backwards, and this is necessary because if they move in a time symmetric movement, then they won't be able to go forward. And since the segments can self-intersect, the creature moves by first tucking one paddle into his body and using the other paddle to push, and then tucking in the other paddle and then using the first paddle to push. And here is a showcase of the pink paddle creature with the one body, two paddle design. And here is a fish creature which has a similar design, but the body has multiple segments which make it move in a sine wave-like motion. Both the pink paddler and the fish have the periodic time asymmetric movement, which is good. So we were able to get fitness graphs for the creatures which measure fitness over generations. Let's take a look at those. So for the purple paddler's fitness graph, the best creature's fitness goes up as they evolve creatures that make them go farther. The medium creature fitness goes up a bit, and the worst creature a lot of the time is a mutation of the best creature, and it makes them go backwards very fast. So, and then the fitness plateauing near the end means the creatures are converging toward an optimal design. And here is a creature that evolved non-oscillatory motion. For oscillatory creatures, note the longer time to converge to a higher maximum fitness. But the non-oscillatory single pusher reached a lower maximum fitness very quickly and is stuck in a local minimum. This creature was able to push itself forward once, but it can't move again. Our code currently doesn't have a method to account for this, so we'll be fixing this in the future. And here is another non-oscillatory creature with similar data.
So yeah, as was mentioned, there's a lot of potential for next steps. We're first going to try and fix that self-intersection via a repulsive force when the parts intersect. Then we'd like to add some extra joint types. Right now, we're only working with fixed joints or a hinge joint. So we don't have motion for multiple axes, that might be limiting our paddling motion. We're of course going to implement that reinforcement learning section. And then for the future, there's a lot of potential with connecting this with more robotic applications in the real world. The idea is to connect it with Ross and Isaac Sim, which allows to simulate tons of these creatures in rapid parallelized form. And you can see a GIF of that in the corner. And finally, I hope you guys would like to use this app to create some stuff. So we're going to try and publish this as a usable app. And to do so, you can join here for more updates. And thank you for listening to the presentation, and we're open for any questions. Okay, let's see, the crossover step we're looking at. Let's see, so that was a step described in the original paper. The way it roughly works is, so you see how the creature's kind of created out of a bunch of different segments. What we do for this is the two parents will be chosen with their own respective graphs, and then the graph will be cut at some point and then spliced together based on some criteria. We didn't look too much into that step as we were mainly focusing on getting standard mutation down, but we already have a 5-step repeated process. There are so many failure cases for this, it is insane. But we've gotten this working. Next steps for the future, absolutely working on crossover. Okay, so we got a question here. How do we find the original paper? This was just found like on YouTube, honestly. There was a video made a couple years after, because this was in 1994, so there was no YouTube. But after that, the work of Carl Sims was kind of collated into a video with some pretty funny, like David Attenborough style, like notation over everything. And it showed some pretty cool creatures. They had a swimming environment, walking, as well as jumping and competing for a block. So that was really interesting. We're looking to add some of those things. And then pivot back to Tame's question, how's crossover different than mutation? Crossover kind of lets you have two parents. Oh yeah, you can talk about it. Go ahead, Epi.
Yeah, so the reason why crossover is quite popular in most evolutionary algorithms is because it's able to increase the diversity inside of a set. Essentially, by having two different parents and combining them together, you can have hopefully the good characteristics of both. So for example, say a creature has lots of paddles that it's swimming with, and one creature has a tail. A crossover might be combining those and creating something with two paddles and a tail. Unfortunately, so with just standard mutation, what we're doing is that there is no like combining of creatures together. You're only you're mutating one creature to create more steps than that. It generally tends to be quite effective. This mutation is quite effective as well. But if we can get crossover working, we would like to have a look at that in the future.
Yeah, and I see, let's see, what kind of qualifications do you guys look for prospective group members? Well, this is our first year running this project, and it's actually my first year at UTMIST, so I'm very thankful to have this fantastic opportunity. I'd definitely like to continue this next year. We've got a lot of next steps possible with Ross and making the app, published, so we can look out for that. I think developer applications open in August, so I'll be putting out probably a revised project statement, and you guys can join the UTMIST Discord server to get more updates on that. But generally qualifications, I'd say a good amount of experience in this stuff. We're working with not only Unity, but also a lot of C# and we're re-implementing the algorithm basically from scratch. We don't have PyTorch, we don't have TensorFlow. It is 5,000 lines of pure C# code. Like we started from the basics. So if we're going to create this thing, you need to be quite capable with really understanding the depths of this stuff. It's really fun as a result. It's a bit laborious and it's a little bit different from other projects, but it's very exciting. But yeah, other kinds of joints. I mean, the original paper had like a really long spiel about joints. It was around 20 different types, and a lot of them don't even appear on the internet. So that was something we kind of wrestled with. We ended up going to just the hinge joints for now, but some other types that were listed involved certain twisting and bending motions, universal joints, as well as constrained joints. So, we're still looking into those. Applications in robotics. Let's see. So the idea for that is basically shifting from, the kind of segments and blocks that we have towards something that could be buildable in robotics. There have been some papers on this, like kind of building a universal descriptive language for robotics and creatures and then evolving within that language. That's definitely like some potential because, let's say we're looking at a Roomba that needs to go around a house, clean different things, get under different obstacles. We could work with our lovely little cylinder that we have, or just give creature evolving a shot. Perhaps we'll evolve something quite efficient. We could add in different parts of the reward, like conserve energy, or be able to get under the couch, but also above this certain section. There's all kinds of potential for that. And there's also a couple other papers we were looking at. One interesting pathway was looking into muscle fatigue. So kind of adding in simulated muscles to get everything really smoothly operating. So that's some other pathways. Is this embodied intelligence? Well, okay, I've not heard of a proper definition of embodied intelligence, but if we take it to be an AI involving within its a body, then I guess in a sense, because you could argue that regular reinforcement learning, if it's already sort of embodied, it's learning in an environment to maximize a task. Like that hide and seek robot, it's able to move around the entire environment perfectly fine, and it just doesn't change its form. So this is a bit like that. The evolutionary step is definitely not as precise or expandable as the reinforcement learning. It's not a giant MLP network. It's actually a very like idiosyncratic style of 22 different distinct neurons. So there's a bit of a big divorce between the field of EA in this paper and the field of RL in this paper. So it's a different combined system, but is it embodied intelligence? I'd say most likely. It's an interesting form of it. Yeah, I think that's all the questions. Let me know if I missed anything. Or if anyone on the team wants to add anything.
Thank you, Andrew.
I appreciate it. Thank you. And I'll send the Discord link again because we're gonna try and get this out, maybe on Steam or something. We'll see. Yeah, okay. Thank you, everyone.
Exciting stuff. Thank you, Andrew, and the team of Virtual Creatures. Really appreciate the work. And your team has always been really passionate and vibrant. So I'm glad that the results are very appealing. And I look forward to any future works from all of you. Next up is our collaboration with a startup, PhotoML. They used to be called PhotoML. Now they're called Photograph First, which they're developing a software that aims to automate the process of professional photo culling, which is essentially the process of choosing and filtering photos in a very big batch. Suppose you're a photographer for a wedding scene. You might have taken 2,000 photos, but you only want to select 100 out of them. So essentially, this software is trying to automate that filtering process using an ensemble of computer vision methodologies. And here with us today is the director of the team, Gerstamar. So let me pass the time to Gersti to present their work.
Right, I hope everyone can see my screen.
Perfect.
Right, so yeah, as Stephen introduced us, we are PhotoML. We're basically working with a startup to automate the process of image culling. And I think Dave is going to start off with the slides.
Yep, I am. Could you go on the next slide? Okay, so hey everyone, my name is Dev, and I'm super pumped to present what we've been up to over the course of the last few months. Gersmar, Chris, and myself will be speaking to our collaboration with PhotoML or Photograph First. So prior to September 2022, the founders of PhotoML reached out to UTMIST with their startup idea of automatic photo culling, and this project was really unique because it was a collaboration with the startup. And PhotoML provided us with computing funds, data sets, and domain-specific advice through consulting with professional photographers as we developed the machine learning solution. Next slide. Now I'm going to speak a bit to the project scope and sort of the overall goal of the entire project. The main problem was that photographers typically take a few thousand images in any given shoot, but only select a few hundred for the final product. And this process of cutting down is known as culling. And culling is a long and tedious process through which photographers select the best subset of images from a larger group of images. And our goal was to make the machine learning model personalized, as each photographer culls differently. Some may have a preference for certain angles or color composition, while others do not. And we wanted to personalize this process of culling by creating an algorithm that could learn how each photographer culls images, then being able to perform culling in a way that reflects their artistic style. And for this project, we set our scope to culling wedding photo shoot. Next slide. And here's a rough demo of what culling actually looks like. So there's a large batch of images, as you can see on your left, and from that batch, a small subset of images are selected, and the rest are culled based on several criteria. And throughout this presentation, we'll be speaking to what this criteria actually is. Next slide. And for our approach, we only knew what kind of output we wanted our algorithm to give. So we sort of worked backward from there. The algorithm sorts images into three different buckets: the certain bucket, the uncertain bucket, and the cull bucket. The certain bucket contains the images that the photographer will choose like 100% for sure. And the uncertain bucket has images that may be discarded or may be chosen depending on what the photographer wants. And the cull bucket contains images that will be discarded. And now I'm going to hand it off to Gerstamar to talk about our duplication detection model.
Right, so we started off with the duplicate detection model. It was one of our submodels. And we very quickly realized that this was a really necessary step of pre-processing, because every photographer would take like 10 or 20 images of the same scene in one go. And they would just continue snapping those images while the subjects in the photo are just moving slightly, maybe closing their eyes and opening them. And they do that to ensure that there's at least 1 or 2 images that they can select where everyone's eyes are open and there's no motion blurring. So when we take in this entire data set of 1,000 images, we need to be able to identify these duplicate groups, because otherwise, if we build a classification algorithm that works really well, it may just look at sets of very similar images and think, okay, well, this image is good, we should select this. And oh, here's another image that looks exactly like the first one, so let's select this as well. And so our final output would end up just being a bunch of images that look very similar to each other, which is why duplicate detection was a really essential pre-processing step. So we start off by taking the entire data set of images, and we split it into different duplicate groups, and we pass each of those groups into the rest of the culling algorithm. And then we select the best images from each group to be in the final product. And our approach to duplicate detection looks something like that. So we essentially start off by extracting features from MobileNet v3, and later in the presentation, we're going to visualize these features using this sort of similarity matrix. And we basically use those similarity matrices at each different layer in the MobileNet features when we extracted those features to determine which layer we should use to perform duplicate detection. And after that, we use PCA for dimensionality reduction, because we had about 1,000 images in each incoming data set, and each one had like 47,000 dimensional vectors, and it wasn't really feasible to do clustering or anything of that sort on that many dimensions. So we first did PCA to reduce the dimensionality of the data, and then we used approximate nearest neighbors to estimate where the duplicate groups lie based on which vectors were close to each other. So I'm sure you're wondering, why not image clustering? The main problem with that is that we did not know the predetermined number of image clusters, because when we get an image data set, we don't know how many duplicate groups will be present in it, nor do we know the number of images in each cluster. So in this case, it was much easier to define some sort of similarity metric between different images, and then estimate a threshold value for that metric. So if 2 images had similarities above that threshold, we would consider them as part of the same duplicate group. So in this slide, we essentially show what our different submodels were and what was the rationale behind each submodel. So photographers would typically look out for many different features when they're doing image culling. For example, the emotion of the people in the frame, whether their eyes are open or closed, the color composition of the image, which includes things like lighting and etc., and as well as the use of the space in each frame. So we wanted to account for each of these features by having a submodel that extracted those features that the photographer would look out for. And then we used those features to essentially somehow make a prediction about which class an image should belong to.
Yeah, so now I'm going to go over more in detail on what our approach to the submodels were. So in this diagram, it's just a refinement of what we just showed in the previous slides, but we're just essentially splitting the culling algorithm into its actual components. So in the diagram, the green shows our pre-trained models and the blue shows the models we trained. And when the images are inputted, they first go into the duplicate detection model to carry out the pre-processing. And then we filter it out into however many n duplicate groups there are. And then for each of these duplicate groups, they're passed into our 4 models on closed eye detection, emotion detection, neural style extraction, and semantic segmentation, which we'll further explain in the next slides. Then all of these detection models and the results are combined into one ensembling model, which result in the certain bucket, the uncertain bucket, and the cull bucket that was explained earlier. Next slide, please. And then, so I'm just going to go over the emotion detection approach that we use. So once we take in an image of a lot of faces and their people, for example, in our scenario, if we see a photo with wedding images and people participating in that wedding, through our face detector system, we detect any sort of faces that appear in the image. And in this slide here, they are showed by green boxes. And then we extract all these faces using an open source library called FaceNet PyTorch, which uses the MT-CNN backbone for detecting and drawing bounding boxes around the faces, which are again showed in green here. And then after that, that's sent into our emotion recognition model. And then so these individual faces are just cropped by themselves without their bodies. And then they're passed through our custom emotion recognition model trained on a large open source data set from Kaggle. And if you look closely on the lower left image here, for each and one of these faces, we give a percentage representing the emotion that is being portrayed by the faces. So yeah, next slide, please. And then now I'm going to go over how the closed eye detection sort of works in our algorithm. So given those faces again, we take a look at the eyes themselves and we extract facial landmarks using the dlib library, particularly the 6 landmarks for eyes indicated from P1 to P6 in the slides. So with these 6 landmarks, we calculate the eye aspect ratio based on the formula shown on the slide, which the basic intuition on this formula is that we take the norm or the distance between 0.2 and 0.6, and then add that with the norm of P3 and P5, and then divide that over twice the norm of the P1 and P4. So the intuition behind this ratio is basically that the higher the aspect ratio, the wider the eyes are open. So this is how we kind of determine if the eyes are closed or not. And then after that, we get the result of the aspect ratio. We pass this number, the output of the year formula, to the binary classification models. Next slide, please. And then in terms of our style extraction, we first deal with the image at hand, and then we flatten the image into a long vector, which discards any essential information about the structure. And this is just done so that we can only focus our algorithm in terms of the style, which would mostly be centered on color. And then after that, after we get that long vector, we multiply the vector with the transpose of itself. And then each element in the resulting matrix or the diagonal matrix is basically the dot product of a color channel with another color channel. And this represents the similarity of those 2 color channels, which is basically just the style of the image, which is how we extract the style from the initial image that we received. And then the same process can also be done with image activations after passing through layers of a pre-trained network like VGG or ResNet. And this encodes for more advanced stylistic features like texture, etc. Thank you. Next slide.
Right, so then we have semantic segmentation. This was also done using a pre-trained MobileNet v3, and it was pre-trained on, I think it was the ADE 20K dataset from MIT. And yeah, there isn't that much to explain here. It was just regular semantic segmentation. So now I'm sure a lot of you are wondering why the submodel approach. And the main reason is that the difference between culled images and selected images is very minor. And it's a very nuanced process of selection. And if we just simply allowed a network to classify images based on features that it learns by itself, then the results would not be as good, because learned features can be very arbitrary and they may not be helpful when the difference between our classification groups is very minute. So that's why we felt it was important to predetermine these features and then select them out. And also another advantage is that it's very easy to add or remove submodels based on what photographers like, and just the fact that we have a very modular structure, which allows us to just add new submodels if we feel like it. And it's also more robust because ensembling prevents predictions from being overly dependent on the outputs of a single submodel. And for this reason, we prioritize reducing the compute time of each individual submodel rather than having more accurate models, because we realized that having models with maybe a 2 or 3% accuracy increase was not really worth it, since we had 4 models that we were ensembling over. So it was just more important to have computationally efficient models. That's why you would notice that we use MobileNet in at least 2 places above. And for model training, we had 2 main stages in model training. Firstly, we passed images through the submodels, and we basically just passed the entire data set through the submodels and obtained and stored these output activations. And then we unified the structure of all of the output activations so that we could pass it in through the ensembling model. And the ensembling model essentially serves to estimate the importances of each of the features extracted from each submodel. And it basically just estimates how important it is to that particular photographer, say the use of the frame or the emotion of the people in the image. So it's specific to each photographer, and the individual stylistic preferences are encoded by the weights of this model. And here's a little demo of what the output looks like. So this is the similarity matrix that I was talking about earlier. And this essentially, each sort of square in the similarity matrix represents the dot product between the features of an image and another image. And you would notice that along the diagonal, we have these really bright squares because that's just the dot product of the features of an image with itself, which is obviously going to be very high because they're the exact same image. But we also see these the emergence of these sort of sub-squares, which are these like 3x3 squares. And we see that those are also much brighter and stand out from the rest of the matrix. And that's because those represent the similarity between images and other images in the same duplicate group. And this is essentially how we visualize the outputs of the MobileNet v3. And layers that had more distinct squares were the ones that were selected to perform duplicate detection, because those help sort of polarize the duplicate detection outputs more. And then we just took those duplicate groups, passed them through each of the submodels, unified the output structures, and then had a classification score for each image that was output. And we see that from this entire data set of images, the ones that have the highest classification scores have been highlighted in red in the on the right side. So our conclusion is that submodels help identify the specific features that we need for image culling. It makes it easier for the ensembling model to learn relevant information. And it's a strong approach, but there is still scope for comparison with newer models, particularly like vision transformers or SWIN transformers. And they may have very good performance in this task because they have the capability to pay more attention to certain parts of the image, which is kind of what we want to do. And we could also experiment by adding more submodels like maybe depth detection or pose estimation, because these are all things that wedding photographers may look out for when they classify images from weddings. And yep, that's the end of the presentation. I believe now we have questions. Actually going to stop sharing because I can't see the questions. Okay.
There's no question, then we will also move on. Thank you so much, Kirsty and your team, for the presentation. One additional information is that this team is actually very huge. There's more than 10 developers, and the presentation here is kind of a subset of what they've been working on, specifically for the ML part of things. There's also a full stack software development team that is currently helping out with the startup on the ML integration side of challenges. But yes, very exciting work, very exciting ensembling techniques. And once again, thank you, Kirsty and your team, for the work and the presentation. Moving on is our Numer AI team. This is a team of UTMIST developers led by Andrew Zhang and Jensi Wei, which is a bunch of people attempting to beat the Numer AI online competition through the use of an ensembling of ML models and a meta model strategy developed by Andrew and Jensi. So Andrew, if you're ready, feel free to share your screen and tell us about your work.
Yep. First of all, can you guys hear me?
Yes.
Okay. Let me share my screen. Okay. Can you guys see the slides?
Yes.
Okay. So hi everyone. I am Andrew. The co-lead for our team. Jensi is currently still not in Canada, so I'll be covering for him in presenting our the current progress in our project. So to recap, our team is attempting to beat this competition that's hosted by the world's first crowdsourced hedge fund. So how it essentially works is that the hedge fund based in San Francisco called Numerai, it provides us with obfuscated financial data that are of very high quality that are published in weekly rounds, and our goal is to perform regression on the published data and submit our weekly predictions as a CSV file to the hedge fund. So this is essentially the competition itself. So why would the hedge fund do this? As you know, high quality financial data is very expensive. Well, the reason why the hedge fund is hosting this tournament is that the hedge fund's AI, aka the meta model they call it, takes every participant's prediction as an input and then churns through every participant's submitted CSV weekly predictions and then help the hedge fund to make investment decisions. And in turn, the participants are rewarded with cryptocurrency if their predictions are indeed accurate. And one thing to point out is that the data that the hedge fund publishes is obfuscated. That the features are given hashed names, so we don't exactly know what the features are. Otherwise, like we could just use their data set to make our own predictions and make money ourselves, not necessarily work for them. And yeah, so this is the nature of our problem. And essentially, our approach is that our team will attempt to mirror the hedge fund's approach. So we will build our own mini meta model within our team. That was essentially our plan. So yeah, so our hope was that our approach would make our project very horizontally scalable and it could accommodate for a wide range of technical capabilities. So the developer in the recruitment process, we try to recruit for as many developers from as many unique backgrounds as possible. We tailored the Numerai experience to be more of a learning experience than a final result oriented sort of experience. We hope so many of our members, they do not necessarily have previous data science or machine learning experience. So we hope from a project they could learn the entire process of constructing data pipelines and working with machine learning models, learn basic machine learning concepts as well. So yeah, our team comes from a very diverse background, both in terms of capability and their academic background. So to give a more concrete understanding of the sort of machine learning objective, here's a more detailed look at what the weekly published data set looks like. So in summary, first there's a bunch of features that, in fact, like there's thousands of features for each data input, and so as I previously mentioned, each of these features represent some obfuscated financial metric. It could be the GDP of the GDP per quarter GDP growth of certain countries, or it could be the stock price of Apple. But no one really knows what they are. There's more than 1,000 of them, and there's also a time series component of it. So these batches of features they're given in eras. Every era is 1 week, i.e. 5 working days, because the stock market doesn't open on weekends. So yeah, and they don't have explicitly defined feature groups, but some features are more correlated with others, as you can see from the feature matrix over here. And what's also interesting is that across different eras, the number of data points in each era is different across. It is different across every era, so that makes the data processing pipeline. So our data processing pipeline needs to be robust to that that feature of our data set. And in terms of target, instead of just predicting one target, so whether a financial asset will rise in value or fall in value, there are 20 different targets. Again, all 20 targets are some measure of how the financial asset will perform, but the only target that the hedge fund requires us to submit is target no mu v for 20. So that's the actual target that they want. But all of the auxiliary targets, they have various correlation with the final target that they expect us to submit, and training your model up on these auxiliary targets will be sometimes beneficial to building submodels to our final ensemble meta model. So yeah, so here I will present some of our preliminary results on building our meta model. So initially we had a survey of what so we gave a very high degree of autonomy to our developers. We let them decide what sort of model that they want to build. So initially this is what our model zoo essentially looked like. So in theory, the theory is that the more diverse range of models that we have, the more power the more powerful the final ensemble model will be. But as we progress with our development, we realized this is not necessarily the case. So all the developers who attempted neural network based models realized that neural network models in general, no matter what architecture you try, tend to perform poorly on the NumRI dataset. And essentially all of our developers at the end converge towards a tree-based model, and this is supported by theory. Those of you who are interested in why this phenomenon arises can have a read of this paper. But yeah, our the preliminary result discovered by our team is that it highly coincides with the result of this paper. Essentially, like on the NumRI dataset specifically, neural network-based models doesn't perform as well as decision tree-based models, specifically boosted trees such as XGBoost and LGBMs. So here so that sort of hindered our progress at building large-scale ensemble models, because the pacing of the developers who have attempted various neural network-based models was hindered by the technical problem that I have outlined in the previous slide. But here are some individual results that are very promising. Again, these promising results are all based on tree-based models. So the NumRI hedge fund has recently released their version 4 dataset, but this is this particular graph is of the version 3 dataset. Yeah, so this particular model built by one of our developers has achieved around the 80th percentile in the diagnostic benchmark provided by the hedge fund of all the participants to the tournament. So this is indeed very promising. As we move towards ensembling, we expect this percentile to be to achieve a much higher percentile than of the individual models. And this is our most recent. This is a more recent benchmark of another tree-based model built by another one of our developers. This is on the V4 dataset, and this also in terms of ranking, this particular model also performs on par with the previous model shown. So these are some very promising individual results that we have. They all come from developers who have like started out with tree-based models. And in terms of future to-dos, we read up on some more theoretical papers on how to proceed with our project. Despite the fact that neural network-based models does not perform as well on the NumRI dataset directly, what we hope to do in the future is that is to have still have all of our developers build tree-based submodels, and then we use these submodels as feature encoders into a recurrent neural network-based feature decoder as a means of ensembling our meta model. And according to what we have read, this should not encounter the same issue as using neural networks directly on the NumRI dataset, and should be a fairly in this manner of ensembling our submodels should be a fairly robust way of trying to beat the tournament, essentially. This is because mainly the tree-based models that does not take temporal correlations into account, and if we so across epochs, if we encode features using our tree-based models, we could then build a recurrent architecture that takes the cross epoch temporal correlation into account. And also, as I previously mentioned, we give our developers a high degree of autonomy, but some of our members have graduated, and others have other significant commitments over the summer. So project management wise, we're definitely looking to recruit more new talent into our team, while also getting in touch with our individual developers who have started out building neural network models, but then like switched to a more tree-based model approach. And yeah, stay tuned for our future works. This is the current state of our project. Now I'll open the floor to questions.
There's a question that perhaps I can address instead of Andrew regarding what's going to be happening next for this project, and in fact also other UTMIST projects. There is going to be like a quick 5-minute session after our final project presentation regarding how you can join UTMIST and what the UTMIST projects generally look like. But long story short, developer recruitment is going to be in September, and director recruitment and topic selection will be in roughly August. There's no other question, then we will also move on. Thank you, Andrew, and your team for. There is one more question, actually, Andrew. Would you like to address that?
Yeah, sure. So okay, so how you earn crypto from the hedge fund is actually a bit more nuanced. Essentially, you have to first invest your own money, and it's called staking. You have to first buy their crypto, and the amount of crypto you have sort of compounds with a positive sort of interest rate if your model performs well with respect to the actual market movement of the financial assets that the hedge funds are trying to invest in, and they deduct a bit of crypto if the correlation of your model is negative with respect to the actual market movement. So there's a significant risk with actually investing into our model where we don't really know how well they're going to perform. Well, on the benchmark, it's going well, but when the Russia-Ukraine ordeal happened, a lot of the models in the tournament actually had results turn negative, and people ran into losses. So we were actually very careful with investing. Like we could participate in the tournament without investing in terms of just looking at how our model performs and not earn any money, and just approach it from the machine learning perspective. And this is currently what we're doing.
Thank you, Andrew. Due to time constraints, we
thank
do
you.
have to move on. But yes, thank you for your team for the hard work the entire year and your presentation. I'm guessing that it's likely that this team will continue to recruit in the future years. But again, stay tuned for that. We really hope that this team could serve as a platform for any future developers to learn about ML techniques and just the whole topic in general. All right, and let's move on to our final project of the day, OSU, which is a pretty ground up attempt at solving the OSU beatmap generation, which involves kind of taking in an audio sample and generating a beatmap based on a very OSU specific language that the team created themselves. And they hope to frame this problem in a way that is learnable by a transformer-based model. It's a highly technical project. So without further ado, let me pass on the time to, I believe, Alec, which will be presenting the work on behalf of the team.
Hello, can you guys hear me?
Yes.
All right. And can you see the screen?
Yes.
All right, so hi everyone, I'm Alec, and Wei-Han and I will be presenting our progress for the OSU beatmap generation project. And in this presentation, we'll first go over what OSU is, then the methodology we are using and like the models we're training, some current progress, the challenges we faced, as well as the future steps that we have in our project. So first of all, what is OSU? OSU is a rhythm game that originated in 2007, and it contains 4 game modes: Standard, Mania, Taiko, and Catch the Beat. For our project, we will be focusing on OSU Standard. So this game mode combines precise timing, hand-eye coordination, as well as musicality. Players have to move the cursor and click on circles to the beat of the music. And there are 3 object types: the hit circle, which is seen in the picture on the right, sliders, and for these, the user has to follow the track until the end of the slider, and as well as spinners. So our goal is to generate a beat map and get it ranked. So all the levels in the game OSU are called beat maps. And what makes OSU interesting is that all the beat maps are created by the player base. And to get a beat map ranked, people will have to vote for your map to be ranked and then nominated by 2 designated beat map nominators. So basically, we have to make a beat map that other people think is good enough to be a ranked map. And we believe our goal can be achieved using transformers. We took inspiration from MT3, which is a multi-instrument music transcription paper. And we first start off with a reproduction of the paper, or like sort of a reproduction. We only used piano music using the Maestro dataset. And our accuracy was around 10% short of the reported accuracy. However, we took many ideas from this paper regarding how to generate a language, and as well as how they tackled long segments of audio. So basically, the MT3 model is a basic transformer encoder-decoder model. And what was novel in this is the fact that they had their own sort of language with their own grammar. And in this case, they take the audio and they transform it into these series of tokens. And you can see that each token has a different meaning. So there's like time tokens as well as the note or the instrument. And they actually trained on 2 seconds of audio at a time. So what we have done, we first scraped a data set of about 80,000 ranked beat maps. And for now, since longer beat maps are hard to use due to memory constraints on our GPU, we limited to short songs, which are 1.5 minutes or less. And this shrinks our data set by around 50%. So we have about 40,000 maps. We created our own beat map visualizer so we can visualize the results that we generate. We also created a way of parsing a beat map file, a OSU beat map file, to be usable by our program and by the model. We also experimented with a bunch of language representations of a beat map. For example, we tried a language where we used absolute timing versus relative timing. We also trained a encoder for the MP3 files, or actually the input would be a spectrogram. And we found that it's really hard to use a single model to predict everything about the beat map. And we tried training a different model to predict when the user has to hit a beat. And finally, we did some training of the entire transformer model to produce some maps. So an example of language. So this is the first language we came up with. We had different tokens for each aspect of an object. So for example, this is a hit circle object, and this will be represented by 4 sequential tokens or words. So the first one would be the time, then the X position, Y position, and finally the type, which is a hit circle. However, for a different object, let's say the slider, it has to be represented using more tokens, since it has extra information such as a length, as well as the end position.
So
now
where
I'll
we
pass
are,
it on to Wei Han. Yeah.
Sorry. So where we are currently, essentially we're representing each OSU object using a fixed size vector instead of using individual tokens. And then essentially we're using a multi-headed MLP. So as you can see on the diagram on the right, we have a transformer, and the output of the transformer gets split. Essentially, you pass it to different heads of the MLP, and the number of heads of the MLP depends on the number of features that we have. So at time t+1, each of the MLP would output a probabilistic distribution across the number of classes of each feature. So for instance, for the time feature, we have 20 classes. For the object type, we have 7 classes. As Alec mentioned previously, you have a circle, slider, and then a spinner. And also, a slider, you can break it down into different types of sliders, so on and so forth. And then next slide. Yeah, some of the challenges that we've been facing throughout this project is that timing in OSU is just very difficult, and there's a trade-off between the accuracy and the complexity of the language. And also training transformers is just difficult because it's very sensitive to hyperparameter tuning. And we're getting some of our results suggest that the longer we train, actually the performance gets worse. And we also get like NANs, as you can see in the bottom right graph. Next slide. Another set of challenges that we've been facing. So Alec mentioned that a little bit. So currently the audio that we're dealing with is very long, and also the beat map is also very long. So these 2 points combined may put a constraint on our GPU memory. Furthermore, we're also it's also difficult to augment our data because of the essentially the beat map representation. And then if we use a higher more higher level like language representation of our beat map, then it might not 100% encode the features that we want to encode. And then finally, we found out that the loss function that we're using might not be optimal. We added a little example here at the bottom. So say for instance, the ground truth, you have at time t, it's like a hit circle here, and then at time t+1, it outputs a hit circle above the hit circle at time t. But then our model, if it predicts like the hit circle downward from time t, it would incur a high cross entropy loss, right? Because the position is different. But in reality, like for a normal OSU player, it shouldn't make a difference too much, because it's like it doesn't really matter whether the output is up or down. But the cross entropy loss, that doesn't capture that. Next slide. We also did a little bit of ablation study on the S4 model. So as Alec mentioned previously, timing is very difficult. So we wanted to use a different model to predict like timing, also beat timing. So the S4 model takes into input a spectrogram and outputs an OSU beat. So when the player has to click, as you can see from the set of results on the right, the loss is going down, but we have the precision and the recall isn't too good. So precision is peaked at around 70, and the recall is like extremely low. It's actually below like 15. And then we also tested other configurations of the S4 model. So we added like conv layers, some of the like batch normalization and that sort of stuff, but it didn't really improve the performance by much. And then in terms of next step, so I guess the two most important things that we are focusing on is just the hyperparameter tuning for the transformer model, and also the language representation. So these two are the most important items. And then right now we also don't have any generated results, so we're working towards that, and also add like an audio player for the visualizations. The fourth item that we have is essentially post-processing the generated beat maps. So before we submit a beat map to be considered a ranked beat map, there's a set of guidelines that we have to follow, and those guidelines, we're trying to maybe post-process the beat maps more manually, just see like if there's like, you know, incorrect timing or incorrect rhythm, and then before we submit them for review. And then our goal essentially is to get the beat map ranked, and then extend our method to other game modes such as Mania, Taiko, and Catch the Beat. But in my opinion, it should be fairly easy, because those other game modes, their complexity is not as it's fairly less complex than OSU. But yeah, thank you for listening, and if you have any questions, you can ask them.
There's no question. Then thank you so much, Alec and Rehan, for the presentation. Their team is very, very technical. In fact, they're the first team to reach our compute limit. It's also one of their biggest bottlenecks to have a sufficient VRAM for their GPU of computation. But I really look forward to their results. They're still currently working on this project. I know Jonah is also still working on it. So stay tuned for any further updates of this OSU team in the upcoming summer, or perhaps closer to September. And with that, we will actually conclude today's event. That's our final project presentation. And to kind of finish up and wrap things up, I will just share with you guys some details of what a UTMIST project looks like, how you could join, and what are the benefits of joining us later on in September as a developer, or in August as a director. I'll quickly go through this and not take up too much time. But yes, if you join UTMIST as a project director or developer, there's essentially three big things that you can benefit from. Or I would say three things that accelerate any sort of personal projects that is not from UTMIST. First and foremost is advisors, which consists of UTMIST alumni and our connections built over the past few years with companies like Alta, Penstorrent, Vector, and University of Toronto, Hong Kong University, etc. As an organization, it's also much easier to access faculty connections and PhD members. Other than that is compute. This is something that perhaps working on a personal project may be the most difficult nowadays. We have Penstorrent hardware coming to UTMIST very, very soon. We also have a certain amount of compute budget for Colab or paper-space cloud computing. And on top of that, we have two A4000 GPUs borrowed from the U of T Teaching Lab Center. And finally, this is something more for future directors if interested. We will be implementing project management strategies and trainings in about August. This will involve Agile PM training for newly recruited directors. And things that we've always been implementing are things like biweekly internal progress updates and termly external review sessions, where we kind of have the opportunity to present the results to our external connections and receive some valuable feedbacks. We also have a front-end development team that's working on websites for each of these projects. These websites will be ready very, very soon over the summer. And again, stay tuned with UTMIST servers and social media for any updates on those personal project websites. Finally, we are looking at a lot more company collaborations in the future. It is a really new initiative that we started in 2022, and we really hope to continue and expand these collaborations. These are just a small list of companies that we are currently in discussions or already collaborating with. And we're also in discussions with companies like AMD for any potential collaborations in the future. Again, stay tuned. Roughly in August and September, there's going to be a lot of updates on recruitment and opportunities. This is just a roughly description of an internal project in UTMIST. Everything begins in roughly August with director recruitment and their topic of choice. September is for developers. And between September to April, for roughly 6 to 8 months, it will be the main development session. In May, every year we have the Winter Project Showcase. And finally, in September, just a really quick sneak peek, we are planning a UTMIST conference roughly in the second week of September in person, hopefully with more than 400 attendees. This is still in very close preparation, so not a lot of details yet, but it's something that I personally really look forward to. Final reminder, we will be recruiting for VPs, including VP Engineering and the 8 other departments, roughly in June. So if you're interested in that, if you're currently a developer or director, or simply interested in joining the executive team for UTMIST, I highly recommend you signing up for that. And you may become our future executive team. Again, August is for director recruitment. If you have a personal topic in mind, fill out our application, have a one-pager ready of a description of what you're trying to implement. And once you come here, if we really believe that your project is feasible and novel, we will help you do developer recruitment so that you could undergo our 6 to 8 month development cycle. Finally, if you're just a developer hoping to join a really interesting project, that will happen in September 2023. And with that, thank you all for joining the annual project showcase today. Hopefully it was really enjoyable, and I really look forward to seeing you all join UTMIST in the future. For people that are currently already in UTMIST, thank you for the hard work in the past year. I really, really appreciate it, and I look forward to working you all in the very close future. Have a great summer, and thank you for joining.